bramble, which is apparently in reference to the animal's spiky proboscis. I looked it up because I thought there is no way that word is not some sort of British chicken scratch. But according to the Cambridge Dictionary, a bramble is a wild bush with thorns. I don't want to call it either of those things. I don't want to keep saying Myritherian, and I don't want to call it bramble snout, so let's just call it Binks. No reason to make this any harder than it needs to be. If you watch the first episode of this series, you might be thinking that Binks is some sort of leftover version of Opabinia, which is pretty surprising because Opabinia was a lone wolf in the abyss of taxonomy for over 100 years, up until last year when Uterora was found to be Opabinia's relative from the same time. Turns out the day that Uterora paper was published, the lead scientist of the paper, named Joanna Wolf, saw a picture of Binks and was like, no fucking way, there's a third one. Would you believe the luck of that? Whether or not Binks was related to Opabinia is still a mystery. They have plenty of similarities: the proboscis, a backwards facing mouth, legs underneath the undulating body flaps. But Binks was alive 40 million years after Opabinia and had 0 eyes instead of 5. This is still practically breaking news. It was only published a year ago, so I will keep you updated. The next Cambrian leftover in our lineup is a Gyrocassis. Absolutely grotesque. At about 7 feet long, they were some of the largest animals in the Ordovician period, and one of the largest arthropods to ever exist, that we know of. The Ordovician blimp, if you will. Let's go over whatever you could call this body plan. Like other arthropods, their bodies were segmented. Each body segment carried with it 2 sets of flaps to move themselves through the water. They also had frontal spines that carried some weird sort of mesh that seems to have been for filtering plankton. This, along with the fact that they were very big for this time period and the abundance of their fossils, have led scientists to assume that plankton was popping off in the Ordovician due to the great Ordovician biodiversification due to the great Ordovician biodiversification event. God. Today, hundreds of millions of years later, we may take plankton for granted. It's just there, all the time, everywhere, and so small. But the explosion of plankton was a big deal for marine ecosystems. Opened up a whole new lifestyle and body style, large and slow moving. Plankton is an all-you-can-eat buffet, everywhere. No need to be fast or maneuverable. Take your time. Kick your feet back. Exchange pleasantries and good-natured conversation. Get as big as you want. Move as slow as you want. Who cares? There's food everywhere, and everyone's too small to hurt you. Life is good. Think about it. All the filter feeders today are bigger than their active predator relatives. Basking shark compared to a great white shark, blue whale compared to an orca. Slow is the way to go. Other lineages took note as well, like the cephalopods, who really got their footing in the Ordovician. The most well-known Ordovician cephalopods are the orthocones, ones with straight, cone-like shells. If you've been to any stores for rocks or crystals or fossils or oddities, you've probably seen Orthoceras fossils alongside the trilobites. They are unbelievably abundant, and they had relatives that got much larger than ever before, like Endoceras or Camaraceras, previously 2 separate species, possibly the same. We're gonna group them together as Endoceras to keep it simple, keep it quick. Big cephalopods with a big straight shell that could get to 18 feet long, dude. They are the largest orthocone cephalopods to ever exist, that we know of. Unsurprisingly, a lot of our understanding of Endoceras has changed since they were first discovered in the 1800s, as it usually does. Early estimates put their maximum length at 30 feet long, based on a shell that was reported to be that big and then was apparently destroyed somehow. But no other shells that long have been found, so for now their max length is 18 feet long. Maybe one will be found in the future and not be destroyed, but for now, it is what it is. As you would probably guess, most, if not all, of the information we have about them is based on their shells, since their soft bodies didn't fossilize. This has led to a lot of presumed characteristics based on their living relatives of similar size, the giant squid. So based on their size, they were initially thought to be apex predators of the Ordovician, using massive beaks to break through the shells of other orthocones and trilobites and arthropods, tearing shit up like nobody's business. But a deeper look into their shells tells a different story. It suggests they were slow-moving, oriented horizontally in the water column, and they swam horizontally. They were also widespread and abundant throughout the Ordovician period. They seemingly played kind of the same role as Agyrocassis, filter feeders, taking advantage of the all-you-can-eat buffet. This may seem like a jump, given the active predatory lifestyles of giant squid today, and other shallow water squids and octopuses, which are, again, mainly active predators. But exploring the deep oceans has allowed humans to understand that not all cephalopods do that. Exploring the deep oceans has introduced us to some just little guys that just trap plankton with some sort of mucus web, or like the vampire squid that just feeds on marine snow, literally just hangs out. So there's reason to believe Endoceras was just hanging out too. And now, The moment you've been waiting for. I kept talking about these new fearsome predators everybody had to adapt to and shit. Armor on fish, spines and weapons on trilobites. The ever dismissive lock and roll. What were their formidable foe? Sea scorpions. Objectively horrific. Objectively godforsaken. Whatever. This period marks the beginning of the rise of the Eurypterids, the scientific term for sea scorpions, because they technically weren't true scorpions, just more distant relatives to the ones we know today. But they sure did look like fucking scorpions, and I'm gonna argue they were much, much worse. Because while the sea scorpions of the Ordovician, like Pentacopterus, got to a measly 6 feet long, others in later periods would become the biggest arthropods to ever exist that we know of, and ventured into freshwater and even terrestrial habitats. But we'll cross that bridge when we get there. We're gonna focus on the now. Pentacopterus is the oldest known Eurypterid out of the 250 total that scientists have described, and was alive about 467 million years ago. They had massive, grasping limbs for trapping their prey, and fossil evidence suggests they got to about 6 feet long, like I said. There was also Megalograptis, slightly smaller at 2.5 feet long, but hey, still at a length that would give me a heart attack if I saw one today. So, a win is a win. They're most well known for those spikes that I don't need to point out, coming off of their third pair of appendages. Personally seem a bit overkill to me, but clearly worked very well for them to find and trap prey, possibly located underground in the sediment. While sea scorpions lived on to terrorize the oceans for millions of years after the Ordovician, the vast majority of life at this time did not make it out. Like I said at the beginning, the end of this period is marked with a massive mass extinction that wiped out 85% of species alive at the time. The second deadliest mass extinction that we know of, just after the Great Dying, at the end of the Permian, which we'll get to in a couple months. You've probably heard that there have been 5 true mass extinctions in life's history, at least since the beginning of the Cambrian, and we're currently entering a 6th. So a true mass extinction is when more than 70% of species alive at the time die out in a relatively short period. So major events, very, very big events. So the Ordovician extinction is the first true mass extinction, and if I were alive during this period, I would have been fucking pissed the way this panned out. There were multiple phases of this mass extinction that had life bopping around all over the place. In the first phase, the Earth got slapped with a global cooling event. Remember, during this period, Gondwana was in the southern hemisphere and making its way over the South Pole due to plate tectonics. That supercontinent, which carried with it an enormous amount of coastal ecosystems, became engulfed in glaciers because of the cooling. This led to lower sea levels, which led to many of those shallow water and warm adapted species to get booted. This wasn't the end of the world, because there were cold adapted species that were doing okay, or more generalist species that could adapt with the changes and made it out. They were chilling for a bit, because that global cooling lasted from like 500,000 to 1.5 million years. Seemed to be smooth sailing. Nope, Earth got slapped with a global warming. The ice age was over and the cold adapted species got kicked to the curb, hung out to dry. Global oxygen levels in the water crashed, so anything left hanging by a thread got strangled with bare hands and spit on. By who though? What caused all this chaos? It seems as though the major villain in this scenario was actually the newly established terrestrial plants. A devastating shock, I know. These plants were interacting with the terrestrial environment in ways that had never been done before in order to adapt and survive. This means impacting carbon dioxide levels in new ways, weathering down rocks on coastlines that released different chemicals and nutrients into the ocean, which fed marine plants, which led to algal blooms that sucked up all the oxygen in the water. The transition of plants to land was a major event, which meant major effects that went along with it. While this initially had horrific impacts on the animal life that still only existed in the water, this transition eventually paved the way for them to follow them onto land. Alright, let's get the global conditions out of the way. Supercontinent Gondwana, as you would probably guess, is still hovering over the southern pole. There was a chain of some smaller continents kind of hovering over the equator. If you remember, during the Ordovician mass extinction, the world was smacked with a global cooling. Glaciers sucked up some sea level, which led shallow water habitats to not exist anymore. But then the Earth looped back around with a backhanded global warming. So going into the Silurian, those glaciers melted, which led to much higher sea levels, and land masses got covered in shallow seas. This made for a nice and cozy expanse for marine inhabitants, and allowed many groups to recover. If you remember, during the Cambrian and Ordovician, the fishes were pretty much tadpole-like in shape, jawless, sucking shit off the ocean floor, and that's all there was to it. So what were the fishies up to now? Well, this is the time they went absolutely berserk. Diversification off the charts. Jaws appeared for the first time. Different types of fins, ray fins, lobe fins, cartilaginous skeletons, jawed fish with armor. Characteristics that were the building blocks of lineages that would allow them to interact with the world in unbelievable ways. Such as me, using my finger to point to my mouth to tell you about the evolution of jaws and lobed fins. Holy fuck. It's like evolutionception. Let's start off with what probably perked your ears up in that list, the development of jaws. This is a weird development because it seems like something that appeared out of nothing, even though obviously it didn't. Recently, for some reason, I've been getting more DMs than usual asking about the mechanisms, the process of evolution. You know, like, I get that whales evolved from land animals, but what? Huh? And I just finished reading The Selfish Gene by Richard Dawkins, so I'm feeling real fresh, and I kind of want to over-explain the development of jaws to use it as an example in this case to help like visualize it. Also, read Selfish Gene if you haven't already. I was probably assigned that in biology class and just didn't read it, and so I just finished reading it for the first time. It's great for understanding this. It's long, so get the audiobook, listen to it like a podcast. Boom. Easy. Okay, so like I said, jaws didn't appear out of nowhere. The classic idea is that they evolved as a modified form of a trait that was already existing in jawless fishes. They're gill arches. Gill arches are structural loops made out of bone or cartilage that support the structure of gills in fish. They've been present in vertebrates since the Cambrian, so have essentially been a component of fish since the beginning of fish that we know of. Gill arches are great for increasing the surface area of the gills, which allows more oxygen to get into their body at a given time. Absorbing oxygen more efficiently is obviously beneficial to the survival of the little guy. So gill arches that are more and more efficient are going to develop over many generations, as variation in that trait in the population will give some an advantage over others. Little guys with slightly more efficient gill arches are likely to survive and pass on those genes at a slightly higher rate than others, and so on. So these gill arches became more modified as time went on, and something strange happened. The pair of gill arches closest to the mouth pushed forward over time for efficiency until they were essentially around the mouth opening, creating some sort of basic form of a mouth structure. Now, these gill arches, which had a primary purpose of getting oxygen into the body more efficiently, served a secondary purpose, providing a very basic and very slight form of grabbing power, giving them a slight advantage over the ones still stuck sucking up shit from the ocean floor with no structure. This provided a blueprint for those modified gill arches to evolve over time, for more efficient grabbing power as generations went by. This developed into a stronger and stronger structure until it could eventually be labeled as a proper jaw by our definition. And of course, remember, these changes happened at an unnoticeably slow rate. Like, you can't expect to watch grass grow if you sit there for a bit, but if you come back a few days later, you gotta mow it. There have been some changes. But like in this case, come back after millions of years, thousands of generations, then you can mow it then. I mentioned this as the classic idea because as technology has advanced, there are new hypotheses developing based on like gene expression and shit. But I'm gonna stick to the classic idea because it's still valid. As of right now, it is still accepted and it is simple and a good example. And hopefully it was a helpful example. And if not, I will eventually try again at a later date. Actually, you might remember that I talked about it before with the brittle stars that can see without eyes in the All-Stars video. Their chromatophore network likely assisted in camouflage and predator avoidance, and just so happened to make an impact on their existing photoreceptor network that allowed them to sense light versus no light. When those two networks kind of pushed into each other, it somehow created some sort of an image, allowing them to see without eyes. The technical term for this is an exaptation, a trait that takes on a function different than its original function. So, back to this particular exaptation. The development of the jaw. It obviously helped fish go bananas. New niches and strategies developed for this cool new weaponry. So, allow me to introduce you to these first jawed fish that appeared in the Silurian, the placoderms. The Silurian was their bread and butter. They developed armor for protection, pectoral fins for balance and stability, and primitive tail fins. And look at that. We still see fins today. And they diversified to shit. Actually, let's draw a little cladogram, a little map, so we can keep track of all this. The development of jaws led to placoderms, and placoderms diversified to shit. So jaws led to placoderms, and placoderms are the ancestors to bony and cartilaginous fish. Yes, from the shark video. Chondrichthyes, the cartilaginous fish we know today as sharks, skates, and race. These are the roots of that lineage. The acanthodians, also known as spiny sharks due to their shark-like appearance, even though they were not sharks. Just at the base of the lineage that would eventually lead to sharks. They first appeared here during the Silurian and existed for like 200 million years, and were found in oceans all around the world. So, very successful group. means complete primitive jaw. The first fossils of them were discovered in China back in 2013. Matter of fact, take a shot every time I say China, because it's going to come up a lot in the next like 2 to 4 minutes. They're seen as a transitional species between more primitive and modern fish due to their particular set of characteristics. Another one from China called Shilinu rostrata. Kind of looks like a dolphin. Really exemplifies the fact that shit got weird almost immediately after Jaws evolved. The bony fish went in a couple directions as well. The ray-finned rat, with fins made of cartilaginous rays. This is most fish alive today. Think goldfish, think blobfish, think my son the deep-sea telescope fish, think betta fish, etc. There was also the lobe-finned rat, with fins made of a series of bones. Think coelacanths, think lungfish, think us. Yeah, these were the ancestors to tetrapods, animals with 4 limbs. That would come a bit later, like Tiktaalik, amphibians, dinosaurs, the platypus, etc. These bony fins eventually led to the evolution of the limbs we know and love today, but we'll get to that in a couple episodes. But let's get back to the name. One of the earliest lobe-finned fish that we know of is called Cerolepis ramiri. Another one first found in China in 1998. They had some pretty gnarly teeth for their time. And the largest Silurian lobe-finned fish that we know of is called Megamastix, which means big mouth blunt teeth. They're pretty much considered the first vertebrate apex predator that we know of, and could get to like 3 feet long, 3 times the length of any other fish alive at the time that we know of. They were also found in, you guessed it, and kind of changed the way science viewed Silurian fishes, because before their discovery in 2014, fishes were thought to be pretty restricted in their size at this time. At this point, I'm sure you are downright exhausted hearing me talk about fish, and I am absolutely exhausted talking about it as well. Let's move on to the spooky shit. Erase. Alright, the strange specimens. Starting off with a group we are already familiar with, the sea scorpions. Yeah, they were somehow still kicking after the Ordovician mass extinction and hadn't even hit their prime yet. These apex predators continued to be apex predators pre and post extinction, and even beyond the Silurian. Their most heinous form during this time was Pterygotus, one of the largest sea scorpions to ever exist that we know of. They could get to about 6 feet long, with fossils found on every continent except Asia and Antarctica, at least for now. Fossil evidence suggests they had a pretty advanced visual system, all the better to see with, as well as extremely strong punching and crushing chelicera, all the better to punch and crush with.
Anyway, I started blasting. Bang!
Suggesting they were, not surprisingly, a high-level active predator. A horrifying trailer for the forms that were to come in the millions and millions of years later, that we will get to in the next period. And what about the trilobites? Yeah, they somehow also survived the land plant apocalypse. They did lose about half of their diversity, which was obviously not great for them, but they did recover pretty quickly and still managed to inhabit every corner of the earth. Except for the poles. So yeah, trilobites were still around, still doing their little lock and roll pose. Here's one that is definitely unlike anything we've talked about so far. Solacina Cthulhu. A more recent discovery from the UK in 2019, and named after the Lovecraftian tentacled monster. It had 45 tentacle-like feet they used to crawl along the ocean floor. As you have probably guessed, based on the fact they were found so recently, we don't know much about them. Scientists figured out they were some sort of early echinoderm, related to sea stars, sea urchins, sea cucumbers, etc. All the weird animals I talked about in the All-Stars edition of What the Fuck Is This? But what particular echinoderm form were they most closely related to? Let's take some guesses. If you had to guess, do you think Solacina Cthulhu would be most closely related to sea stars, brittle stars, sea urchins, or sea cucumbers? Take a good second to think about it.
Gas! Fuck! Gas! Gas, goddamn you! Why won't you answer me?
The answer is sea cucumbers, which might be the most surprising based on appearance. So let me explain how scientists figured this out. They used a 3D reconstruction process called high-resolution physical optical tomography, a name you have absolutely no reason to remember. What they do for this 3D process is grind down the fossil layer by layer and take a picture at each layer, like fucking claymation, you know, like moving it a little bit, taking a picture. So you're left with hundreds of photographs that can be kind of stacked on top of each other to create a 3D shape. It's like 3D printing, but completely opposite. This 3D model of Solacina Cthulhu helps scientists look at their water vascular system, a body system that echinoderms use for fucking everything. Locomotion, food and waste transportation, respiration, an all-in-one system. Like the men's 10-in-1 shampoo that you can use for like toothpaste and also motor oil. Solacina's particular water vascular system had sea cucumber-like traits. So that is the understanding for now. Other than that, what else can you say about a creature that looks like this? Just classic case of a little guy that hangs out. Another strange specimen from the Silurian was Anictozoon, an animal that, like hallucigenia from the Cambrian, was so bizarre scientists initially had it flipped upside down. It was first discovered in Scotland in the late 1800s, but wasn't described, i.e. given a scientific name, until almost 50 years later. Nobody wanted to touch this thing. Couldn't even give it a best guess. The first jab at classifying it, and the scientist who named it, was DJ Schofield in 1937. He understood it as some sort of proto-chordate. You remember chordates, like us and all other vertebrates and tunicates, are a little phylum. Proto-chordates are earlier offshoots that kind of split off before chordates became true chordates. So chordates and proto-chordates have the same characteristics generally, but they go about them in practice differently. They develop differently. Honestly, it doesn't even matter for this conversation because Schofield was wrong. We know that now. But this wasn't known for a long time. So for the next 60 years, Inictozoon was studied even more based on the assumption that they were a protochordate. This was unbelievably confusing, trying to figure them out with a starting point of wrong. You know when you have those really long math equations where none of your steps are making sense and you're doing extra steps that aren't even remotely close to what you learned in the lesson plan, then you go back and you realized the first answer you got in the first step was wrong? That was the study of this creature. Then finally, in the 90s, new, more well-preserved fossils were found and helped scientists realize that they had their shit all mixed up. The previous fossils were all smushed up and laterally flattened. The reconstructions were all turned around and shit. These new fossils were now three-dimensionally preserved. Soft tissues were preserved, and their traits, now in clear view, lines them up very neatly with arthropods, specifically thylakocephalans, an extinct group of crustaceans alive from the Silurian, maybe Ordovician, to the Cretaceous. Finally, it was making sense. Inictozoon and its relatives had bulbous compound eyes and raptorial limbs. Absolutely precious little guys. Alright, I now want to introduce you to my favorite Silurian strange specimen, Aquilonifer spinosus. That doesn't sound right. Aquilonifer spinosus. What is going on here? It was found more recently in 2016 in the UK, and this is the reconstruction we're now working with. Definitely some sort of arthropod, right? With appendages coming off of each segment, kind of like centipede or millipede-like in form. Real thick antennae that kind of look like they each have individual sentience. And then weird bulbs attached to long threads attached to their back. Are those parasites? Is this some sort of unusual plant-animal combo? A symbiosis of some sort? No. Those little tether balls have been determined to be babies. And the main guy those bulbs are attached to is the mama, or papa. This is an individual with its 10 juvenile offspring attached to it by long strings. A parenting style unlike any we're familiar with in the natural world, but that we can definitely draw parallels to in the classic American mall. The parents with kids on leash backpacks. Kids can have fun and not stray too far from their parents, find themselves in any danger. Parents can go about their business without the weight of a child on their back. Of course, there's always a chance that I or any other passerby will trip over the kid, but that's not my problem. That's on them. Aquilonifer spinosus was named after their resemblance to kites. Their name means kite bearer. I like it a lot, to be honest. I feel like I can imagine what it would be like to crawl along the ocean floor with creatures attached to you by string. I'm imagining it right now, and it feels really natural. I feel like I've done it before. I think I was maybe this in my past life, and I honestly don't mind it. Alright, we're moving on to the next section of the video. I mentioned in the introduction that a major event that happened in this period was the invertebrate migration to seemingly inhospitable habitats. The habitat in question was land. While we humans enjoy a crisp autumn morning or a summer breeze in July, the transition to land might as well have been hell on earth, and a journey our own ancestors, the vertebrates, wouldn't be ready for another 50 million years. Some arthropods, though, just felt like they saw what they needed to see in water, and they're done that, and were ready for a new challenge. One that had dry, suffocating air, gravity on full blast, desiccation around every corner. But it was a habitat of opportunity as well. Plants to feast on with no competition, no predators lurking in the shadows. Very promising. These arthropod pioneers had a long road ahead of them. Lineages had to go through small changes that built up over millions and millions of years to allow them to live on land full time. Their exoskeletons evolved to be waxy and waterproof to prevent desiccation and evaporation. New respiratory structures emerged, etc. One of the first full-time residents called Pneumodesmus pneumoni, a millipede-like myriapod. So millipede relative, but not millipede. I talked about them in one of my first YouTube videos, millipedes, so I'm just going to give them a quick little rundown. If you want to learn more about them, go to the video. Pneumodesmus pneumoni was a pretty typical millipede, even though it wasn't. But this fossil had openings all over its exoskeleton called spiracles, which proved to be a very crucial find for the invertebrate transition to land. Spiracles are tiny networks of tubes that allow air to diffuse into the bodies of arthropods, specifically myriapods and insects, a working terrestrial respiratory system. These networks would end up playing a huge role in the evolution of arthropods, especially, most notably, in the Carboniferous period, which we'll get to in a couple episodes. While Pneumodesmus numini is the earliest terrestrial arthropod we can put a name to, there's trace fossils that have been found even earlier than that, possibly even going back into the Ordovician, which I mentioned in the last video. These are tiny little footprints, some of which have been found in the largest organisms on land at the time, the giant fungus called Prototaxites. It could get to 26 feet tall and 3 feet wide. And no, I will not be hearing anybody out. Prototaxites was first discovered in the mid-1800s and was later described as some sort of giant rotten conifer trunk. We now, of course, understand that trees didn't exist yet, that we know of, but this was the 1800s. They had very few puzzle pieces to work with. Later attempts to classify them included giant marine algae, lichens, or even rolled up mats of liverworts. It was a pretty gnarly debate for like 160 years, until just the last couple decades where now a general consensus has been reached for team fungus. Scientists have been able to detect specific carbon isotopes in the fossils that point to fungus rather than plant. So, giant fungus. Exactly what this fungus looked like is more of the debate now. At one point, I think scientists were playing around with the idea that they could have looked like giant mushrooms, cute little head, which would have been sick. But I think gravity and the lack of fossil evidence removes that possibility, unfortunately. The most common reconstruction is this skyscraper look, which is definitely what they would have looked like to the only animals on land at the time, the little millipedes. The orientation is based on their similarity to tree trunks, but new evidence suggests that they were just as likely to grow horizontally as they were vertically. And of course, the network they had underground must have been fucking nuts for how big they got. So they were probably growing, who knows, fuck which way all over the place. The Silurian was a big time for plants too, evolving systems that would eventually allow them to grow so big we could drive a fucking car through them. So I think the best person to explain this monumental time for plants is the plant expert, Joey, from Crime Pays But Botany Does It. He must know, like, every single plant, dude, and he's a total badass. Luckily, I was able to track him down while he was on the road to put a little clip together for this video. If you don't know him already, you're gonna fucking love him. So, here he is talking about prehistoric plants.
So today we're going to talk about the Silurian period and the plant life that existed on Earth's surface at that time. And there wasn't a lot, at least there's not a lot that we know of, only a few dozen genera. But first we got to talk about what Earth's atmosphere and landscape were like at this period. Now keep in mind there wasn't much soil yet. Okay, to get soil you need weathered rock and organic material. The weathered rock part is easy, there's plenty of rocks exposed at Earth's surface, of course, at this time, but the organic material part is a little bit trickier, okay? It's thought that most of the organic material, if there was any, came from decomposing lichens. Now, of course, the lichen's just a symbiosis between an ascomycete fungus, generally speaking, and an algae. The fungus kind of farms the algae, if you want to think of it like that, but there's no plant life involved. But they can weather and break down rock, and then, of course, when the lichens die, that eventually would build soil. That's an organic material to actually build soil with. But regardless, there probably wasn't a lot of soil, and it wasn't very nutrient-rich or very deep. Certainly, those plants had their work cut out for them. Oxygen levels were certainly a lot lower at this point too. Today they're at 21%. In the Silurian period, they were roughly around 14 to 15%. CO2 levels back then were also 10 to 15 times higher. This would have been a very uninviting place for any vertebrate alive today, right? It'd be choking, suffocating, and extremely warm. That said, this is when plants are thought to have really gotten going. The first plants stayed kind of close to the freshwater, little inland estuarine systems that they're thought to have evolved out of. None of these got very tall, okay? These kind of formed dense, probably what looked like a taller shag carpeting of green around the margins of some of these freshwater ponds. Now, the two most famous genera are the genus Cooksonia and the genus Baraguanathia, both of which had vascular systems, which is pretty impressive. They had internal plumbing. So these were vascular land plants, Cooksonia and Baraguanathia. Cooksonia looked kind of like a whisk fern today, just a leafless green photosynthetic stem with little cups bearing sporangia at the distal ends. It probably topped out at 6 to 8 inches, in some cases maybe 12 inches tall. And Baraguanathia looked like a big green pipe cleaner, kind of more akin to today's lycopods, like Lycopodium, Lycopodiella, etc. But either way, these were not astoundingly complex photosynthetic life forms. I mean, for the time they were, but compared to what we think of today, these were not that complex. Caia was another genus. C-A-I-A was a non-vascular plant from this time period. Zosterophyllum is another one that actually had, I think, Zosterophyllum had a vascular system, but either way, it was just one of these, green pipe cleaner looking things. But think of all the plants that we'll never know existed because they never got fossilized, or the rocks that they were fossilized in later got destroyed. I mean, it can be kind of a trick to find rocks that that are from that actual age of Earth history. Totally different time period. I mean, it would look so foreign to anything that we know of today, and that's kind of what has me so fascinated with it. I mean, just to imagine what those ecosystems look like, and also to imagine what was evolving and what the selective pressures and the environmental stresses that these things had to deal with back then. I mean, especially CO2 levels and heat, and then just the lack of soils too. I wonder what humidity was like too. That would be a weird thing. You know, moving from water to land and having to deal with the threat of drying out, the threat of desiccation. That's a whole other palette of environmental stresses and selective pressures that can direct your evolution. So either way, totally different time period to think about. Might as well be another goddamn universe, but fascinating nonetheless. And again, we've only got a small glimpse of what was actually going on back then. It's like trying to put together a 1,000-piece puzzle when you've only got 9 or 10 of the pieces. So anyway, that's all I got for you today. Have a good rest of your day. Go fuck yourself. Bye.
A phenomenal sign-off. That actually really sums up how the Silurian period ended. Periods that end with some sort of extinction have a pretty clear-cut boundary on where one period ends and one begins. Kind of visualize it in the rock. The most extreme case being the KT boundary, with the asteroid going all over the place. The iridium in the asteroid that wiped out the dinosaurs can be seen all over the world. The Silurian didn't have this. Kind of just ended. Kind of a go fuck yourself to scientists, because they had to get a boundary internationally recognized by a committee of specialists, which didn't happen until 1977. They marked the end of the Silurian and the beginning of the Devonian by the first appearance of a graptolite species called Monograptus uniformis. Graptolites are colonial animals, and this particular graptolite species first appeared about 419 million years ago, in association with some trilobite and conodont species. Whatever. It's just complicated, and that's the point. But there were some minor extinctions that happened throughout the Silurian, specifically 3, that played over a time span of like 10,000 to 200,000 years. The first one was a global cooling event that also had a huge drop in deep ocean oxygen about 434 million years ago, leading to the extinction of many deep ocean and open ocean species like conodonts, trilobites, and graptolites. 6 million years later, there was another minor extinction, another oxygen drop that led to the extinction of 95% of graptolite species. Tough shit for them. And the last one, 4 million years later, seems to have been due to a global sea level drop due to glacier formations that wiped out a shit ton of graptolites and some additional conodonts. These extinctions likely played more of a local role than a global one, but were extinctions nonetheless. By the end of the Silurian, the Earth was ramping up to introduce the largest predators the Earth had ever seen that we know of. As always, we're gonna get the global conditions out of the way. This is gonna look fucking sick now. During this time, supercontinent Gondwana was finally headed north, away from the South Pole and ready to see other parts of the world, taking a nice little loop, like the Royal Caribbean Ultimate World Cruise. And finally, Gondwana had a buddy, another supercontinent right near the equator called Euramerica, which was formed by parts of, you guessed it, Europe and America, and also Greenland and Russia. Plate tectonics, as always, going absolutely nuts. Now that land plants are kind of doing their thing, I feel like it makes a lot more sense for me to introduce what the fuck they got going on at the beginning of the video to kind of set the scene. Probably should have been doing that the whole time, to be honest. Makes more sense for the flow of the video, but what are you gonna do? Okay, so in the Silurian, we had those vascular plants that were starting to evolve that Joey talked about, Buxonia and whatnot, the shag carpeting on the riverbanks. And then, of course, the massive fungal towers that early invertebrates called home, like Prototaxites. But during the Devonian, the plants started to spread out beyond the wetlands, and Prototaxites got booted. They got replaced with the next major development in terrestrial plant life, the first large trees and forests. Yeah. Shit was kicking. This is the time plants started to get more comfortable with more rigid support structures that we know today as wood, which was great for early land animals who had found home in the fungus. Luckily, bitches love wood.
That's what she said.
Now you might be thinking, Lindsay, you said these were the first large trees and forests, but really, how big were they? They couldn't have possibly been that large so soon after the first development of wood. Well, I like where your head's at, and I can almost guarantee that there were lots of, if not mostly, pipsqueak trees. But the two that I know about, the more well-known trees of the time, were actually fucking massive. How do I pronounce that? Wadiza. The first one is called Wadiza, and is known as the world's first tree that we know of. It got to about 30 feet tall and kind of looked like a palm. And the next one, Archaeopteryx, not to be confused with Archaeopteryx, the transitional dinosaur bird. I know they sound fucking identical. Archaeopteryx, the tree, was one of the first true trees with that classic woody trunk. And they could get to like 80 feet high that we know of, which is fucking insane. Both of these trees use spores to reproduce instead of seeds, because seeds were not a thing yet. Spores are what algae, fungus, and ferns use to reproduce today. It's kind of like the OG reproduction method of fungus and plants. Seeds do seem to have evolved during this time, though, with the first gymnosperms. Let me make sure I pronounce that right, because I always get plant shit wrong.
Gymnosperms.
Gymnosperms. Got it.
Got it!
That's all the plant stuff I have for you right now. If you have any questions about other plants or wood, don't ask me. I need an in-house botanist because I am out of my comfort zone talking about plants. I am hanging on by a thread. So, let's move on to something I'm more comfortable with, the animals. You might have seen this fish in a variety of meme formats. We've arrived at this time in Earth's history. This is Tiktaalik, considered the true transitional considered the first true transitional fossil between fish and water, and tetrapods on land that would eventually evolve into amphibians, reptiles, birds, fish. Not fish. Not fish. Why did I write that? Why did I write that? That's ridiculous. Mammals. Us. That's the list. The Devonian land was finally getting its vertebrates. It was the end of the no-bone zone.
Do not compare my exoskeleton with your fucking bone!
Before I get ahead of myself, let me get some general information out of the way. Again, I want to define tetrapod. Tetra, 4, pod, legs. All the vertebrates on land have 4 limbs, or legs, or at least had. If you remember in the last episode, I talked about the development of ray-finned fish and lobe-finned fish. The lobe fins holding those prerequisites that their tetrapod descendants would use to haul themselves onto land. The common ancestor of both the rays and the lobes had these things called air bladders connected to their throat that we now know in fish today to be the swim bladder. Helps with buoyancy control. The ancestors to tetrapods went a different route though. Their air bladders evolved into lungs. It might be weird to try and imagine what this would look like in a fish with lungs in a fish, but luckily we have a living fossil example of what this looks like. Lungs in a fish. One of the tetrapod lineage's closest living relatives, you guessed it, lungfish, which have gills but also have lungs to breathe air, which they absolutely need to survive. They can live in dried up patches of mud and haul themselves onto land to get to a different piece of mud if they need to, and they go about it in a pretty grotesque way. And the ancestors to tetrapods probably started moving onto land in a similar fashion about 390 million years ago, that we know of. And with more and more time spent from shallow water onto land, came more and more adaptations to be comfortable there. At first, their skulls became flatter with their eyes situated on the top of their head to spot food and foe from above the water line in their shallow environments. They also got a neck, or range of motion to look around. And of course, over time, their limbs became stronger and stronger to let them move around land with ease, since clearly, getting around like a lungfish is not the ideal terrestrial form. The coolest part about this transition is all of the transitional fossils that scientists have found that literally show a gradient of characteristics from water to land. Tiktaalik is the most famous of those because it was kind of the missing link for a long time, and the story of its discovery is absolutely insane. So I actually decided I'm gonna make it a separate video that I'm gonna put out next week because it honestly deserves its own spotlight. I remember learning about this discovery in college and having one of those moments of like, holy fuck, science is so cool. One of the discoverers of Tiktaalik, Neil Shubin, has a couple videos on YouTube where he was either interviewed or giving a presentation just talking about the discovery, and he is so just clearly passionate about it, and it's so cool to watch. So I'll link one in the description if you want to hear about the discovery from the first person point of view before I present it next week in the third person point of view. So I actually don't have much to say about the arthropods that made it to land in the last period, which is shocking because in the next period they are fucking taking flight and they are massive, and it is complex and huge and massive. So it's thought that flight in insects, and also insects in general, must have evolved during the Devonian or even earlier, but trying to find evidence of that is like trying to find the tiniest needle in the largest haystack in the world. They may be the most successful lineage today, but they are very small and weak as shit. There was at one time a fossil that was thought to be the oldest fossil insect called Rhinognatha, discovered in 1919 as a little tiny partial head with preserved mouth parts, found in rocks about 400 million years old. It seemed to be an insect based on those mouth parts, and later specimens found from the same site had even more of their body preserved, and they seemed to be some sort of wingless insect, such as today's springtail looking thing. And so for a long time, this was considered the earliest insect ever found. But then, over 100 years after its discovery in 2017, the specimens were reanalyzed to be some sort of myriapod, the group that includes centipedes and millipedes, and we already knew they were bopping around, so now we got nothing that I know of. For now. This is just to say, prepare yourself for the massive leap that is coming in the next period. In summary, there were millipedes, and then muddy, for millions of years, and then boom, 3-foot-long dragonflies. Next, moving on to the trilobites. They were still kicking. That's all there is to that. But I promise the rest of this period was not so mellow. Like I said, there were still some specimens that were weird as fuck. There's always strange specimens for a variety of reasons. Maybe they look like aliens. Maybe they're bigger than you're comfortable with. Maybe they're just simply heinous. Luckily, the strange specimens on today's lineup hit all of these. And to really build the suspense, we're gonna get bigger and bigger as the video goes on. So, starting off with the smallest on our list, how do I pronounce this? Mymetaster. Let's just go with that. Good thing, so let's just go with that. Allow me to introduce you to Mymetaster, which kind of looks like some sort of crab spider on a bad acid trip. This was, you guessed it, an arthropod that could get to about 5 to 6 centimeters long. So, just a little guy, but heinous nonetheless. Remember from the Cambrian episode, there was an arthropod that kind of looked like this? Morella? Well, they're actually considered to be related to each other. You can probably think of Mymetaster as like Morella's Wario, but they had a lot more going on than that. Since they were first described in 1931, Mymetaster's fossils have almost always been found in association with either a sponge or little cone cephalopods. They also seem to have lived in little groups. They were very social, very popular. They valued friendship and helping thy neighbor. It seems as though sponges used them as a hard substrate to settle on. And the little cephalopods, I don't know, maybe they were just hanging out. So, even though Mymetaster looks like sudden death visuals, they seem to have been pretty chill little guys. Alright, the next little guy on our lineup got to about 10 centimeters long, so still teeny weeny. It's called Schinderhannes. I think that's how you pronounce it. Another arthropod that was named after the 18th century German bandit, cause yeah, I can definitely see the resemblance here. Right off the bat, I'm sure you're thinking it looks right out of the Cambrian, even more so than the last one. What is it about them that makes them look like a Cambrian creature? In the paper that announced its discovery, scientists mention it's the prominent limb, or claw, at the front of their head that makes them look like a Cambrian creature, which they call the Great Appendage.
That's what she said. Don't you dare.
I can already smell the comments coming about this one. A lot of Cambrian arthropods had the Great Appendage, like Opabinia, Anomalocaris, etc. And then boom, here's another one from 100 million years after that. At the time of its discovery in like 2009, this was a really big deal. It was thought the Great Appendage forms went extinct at the end of the Cambrian. It's still a big deal, but since then, Neorethiran was found, discovered from the Ordovician, so there's just a better understanding now that the Great Appendage did not disappear, as some had thought, and lived longer than we could have ever imagined. All right, we're gonna jump up quite a bit from 10 centimeters to 6 feet long. I know that's a bit jarring. Another arthropod in a heinous form we're already familiar with, Acutiramus, a sea scorpion that was found in oceans that are now North America, the Czech Republic, and possibly Australia. Australia is unconfirmed for now, but it would fit right into the brand. Acutiramus was one of the major predators of its time, with massive claws to rip their prey to shreds. Early overestimated calculations placed them as the largest sea scorpion to ever exist, until 2007, when a fossil claw of one of their relatives left them in the dust. Finally, we have arrived at the sea scorpion I've been waiting to talk about for 6 months.
My time has come.
Gecalopterus, the largest sea scorpion to ever exist, that we know of. Based on body size calculations from that 2007 claw, they could get to 8 to 9 feet long, dude. That's the length of 36 average scorpions today in a single file line. We don't have shit like Gecalopterus nowadays. So just how big was this claw that changed everything? The preserved length was about 14 inches, just over a foot long, but it gotten kind of chipped over the millions of years that it spent in the rock, so we're missing about a quarter of its length. So in life, it would have been 18 inches long.
That's what he said, right, guys?
And then scientists used the cross-multiply shit that we've talked about before to figure out a good estimate of their total size. You know, comparing proportions to their confirmed relatives and whatnot. Why exactly they got so big is not totally understood. And before you say oxygen,
Stop! You violated the law.
I must stop you right there. That only applies to the giant insects and other related arthropods in the Carboniferous, which I have hinted at probably an annoying amount of times at this point. And yes, sea scorpions were arthropods, but they were not terrestrial arthropods during the Carboniferous. We're not there yet. We'll get to that in the next episode. So, Gecalopterus and other sea scorpion size is still a bit of a mystery. It's thought that Gecalopterus lived in fresh water rather than the ocean. So, more of a lake scorpion than a sea scorpion, if you will. Which honestly kind of makes him more heinous. I don't know. In my opinion, that's worse. Lake animals freak me out way more than ocean animals. Like the fucking giant catfish dude. Holy shit. Lake horror movies are much more scarier than ocean horror movies, and I am willing to die on that hill. It's the murky water, I think. I don't like the murky water. It freaks me out. Okay, so Gecalopterus probably felt like the end of the strange specimens. Kind of wrapping up the video. But if you look at the time left, that is definitely not the case. We are nowhere near the end, actually. Which means, yes, they are gonna get even bigger. And speaking of creepy, large freshwater fish, all of the rest of the animals on this lineup are fish. Yeah, the fish are finally starting to take over in fresh and salt water. So let me introduce you to the next strange specimen on our lineup, Hyneria. Hyneria, a giant freshwater fish that got to nearly 10 feet long. Like some of the more primitive species in the vertebrate transition to land, Hyneria had extremely powerful fins, which has led to some ideas that they were somehow able to haul their massive bodies on the land, but that's a big reach. They most likely use them to navigate the shallow and murky waters of their habitat. I personally don't like the idea of a large fish, 10-foot large fish, navigating shallow and murky waters. If you're more uncomfortable with the ocean creatures, you are gonna love the rest of this lineup. First, Titanichthys. They exceeded 15 feet in length and potentially got to 30 feet long. They were found in shallow seas all over the world and were placoderms. Remember the group of armored fish. Luckily, like most giant ocean vertebrates today, it seems as though Titanichthys was more of a passive feeder. In 2020, scientists tested the resilience of their jaws using something called finite element analysis, essentially applying virtual force to their jaws to see if they would break or bend, see how strong they are. Turns out they were weak as shit, which means they were much less likely to be active hunters, which need strong jaws to crush and smash their prey. Nope. Not Titanichthys. Their jaws would have cracked under the pressure. Their results were closer to those of basking sharks, which just hold their mouths open and let small food particles make their way in. Little things such as little shrimps and planktons. They also had really small orbits, i.e. beady eyes, which aren't great for active hunting either. But not all big things from this time were so passive. And this last one on our list, the biggest guy, is an absolute terror. One of the most recognized animals from the Paleozoic, the poster child of the Devonian period. And so for this prehistoric celebrity, I decided to team up with someone who has completely brought him to life. Julian Johnson Mortimer, a world-renowned visual effects artist who has had his animations of the prehistoric world go viral on countless occasions. You might recognize his Leviathan animation or one of his many viral Spinosaurus clips, and I found him by coming across some of his animations of the next guy on our list. I've been following his work for a while now, and dude, these animations send chills down your spine. So I was stoked he was down to help me out with this part of the video. So without further ado, allow me to introduce you to the dunk. Full name, Dunkleosteus. One of the first vertebrate super predators, and the largest predator of its time, with lengths of over 30 feet. Commonly cited in scientific papers. What made this fish a complete nightmare was its armored head. Yes, another placoderm, but juiced the fuck up. And they had extremely powerful self-sharpening jawbones as teeth. This apex predator was able to take down anything it could get its fangs around. And based on biomechanics studies, they were able to open their jaw within a fraction of a second, creating a vacuum effect that sucked prey right into its mouth. I know these fossils look fake and ridiculous, but this is what you get fossilized from a fish that had armor in its head. And actually, nothing else. The rest of the body is a mystery. You've got this tank of a head and nothing else, at least for now. And this has captivated scientists since the dunk was first discovered in the 1800s. Their massive size has been based on comparisons and calculations and math equations and what have you. So now, I have a confession to make. The newest and seemingly most precise estimates of how big they got make everything that I just said about their size a lie.
You really think someone would do that? Just go on the internet and tell lies?
Yes. I deceived you. Just a year ago, a paper was published with new estimates of the dunk's size, based on new and surprisingly, like scarily surprisingly accurate estimation methods. And they shrunk the dunk. Absolutely obliterated it. You might be thinking, Lindsay, why would you do this? Why would you lead me astray? I wanted to make sure that regardless of how much you knew or didn't know about the Devonian and Dunkleosteus before this video, even if you had never heard of the dunk, nothing at all, you would be able to feel the crushing weight of this disappointment from this paper, at least to some extent. How does it feel? I bet it feels like shit, doesn't it? Alright, let's do a rundown of the paper, which if you're like me, you're probably going into it like, how compelling can a single paper be to disrupt a previous scientific understanding so drastically? Pretty fucking compelling, as you will see. It was published by PhD student Russell Engelman from Case Western Reserve University. He argued that the traditional methods of estimating the dunk's body size were shit, because they were mostly based off the body size ratios of the dunk's much smaller relatives, like Coxosteus, who has more well-preserved remains. And yes, quite a funny little name. But get this, there's also a Dickosteus that looks like this. Coxosteus was like 15 inches long, max, much smaller than Dunkleosteus. So Russell was like, it's insane to take the ratios of small little guys and just scale them up and assume that's the big guy. There's no reason to assume it works that way or is accurate at all. Okay, so he identified the problem, but what about the solution? Well, Russell ended up coming up with a body size estimate equation method that seems to not only work really well for Dunkleosteus and its relatives, but also for most, if not all, other fish, which is insane. It's called the orbit opercular length, or OOL. I'm gonna call it the OOL. It's the length from the front of the eye socket, or orbit, to the back of the head. He showed, by applying this measuring tool to literally thousands of fish, that the OOL can really accurately predict the length of the rest of the fish. It showed. that short, stout fishes tend to have short, stout heads, and long, slender fish tend to have long, slender heads. And luckily for us, the dunk's tank of a head can be accurately measured to determine the ewel, and the ewel is much shorter than you would expect based on reconstructions. And using the ewel, Russell estimated the dunk's actual body length to be somewhere between 10 to 12 feet long. Slap! And so likely shaped like a modern-day tuna. Double slap! A catastrophe of disrespect to the highest order, all written out in mathematical models. And guess what else? This applied to Titanictes too. A punch to the stomach, and probably Hyneria, because why the fuck not?
I'm tired, boss.
Russell Engelman dumped a jar of marbles onto the floor of the prehistoric fish department, and a vat of oil as well. As disappointing as it is to hear that Dunkleosteus is now Chunkelosteus, Russell's new model is a huge deal. Being able to accurately predict the sizes of literally almost every fish is going to be huge for paleontology. It's a big deal for fishes everywhere, so I'm excited to see who else gets wrecked with this model in the future. There's another wreckage I have to tell you about that happened in the Devonian, and that is the end of it, the late Devonian extinction, the second of the big 5 mass extinctions in the history of animals that we know of. It lasted for about 25 million years and wiped out 70% of all species on the planet, mostly affecting marine life through different periods of global cooling and anoxia and etc., or reduced oxygen in the oceans. Marine life was getting slapped around like a ping pong ball, and many species couldn't keep up. Fossil evidence suggests there were up to 10 distinct extinction events that each had a unique impact on different ecosystems, and each had different causes. Just bad luck after bad luck after bad luck. One of the periods of reduced oxygen could have been due to volcanic activity, which also could have led to a global cooling. There was also an asteroid that seems to have pummeled into Earth at some point during this time as well. A nearby supernova is thought to have flashed UV radiation into a hole in the ozone layer based on evidence of some weirdly formed plant spores that seem to have DNA damage. There's also some scientists putting the blame on plants again. Their new developments in land takeover led to some atmospheric changes. Long story short is, the last 25 million years of the Devonian was a clusterfuck, but luckily some species made it out alive and evolved into some more familiar forms coming in the next period, like amphibians and sharks, and some weird as fuck specimens that are gonna blow your mind. We're going to start off by getting the global conditions out of the way. So back in the Devonian, we had supercontinent Gondwana in the southern hemisphere, and then its buddy, supercontinent Euramerica, kind of situated at the equator, just above it. Well, in the Carboniferous, Gondwana was really cozying up and started moving closer and closer to LaRussia. Now you're probably thinking, wait, what the fuck happened to Euramerica? I was thinking the same thing. Who's this new LaRussia character? For this section, the continental tectonic shit section of this series, I tend to keep the sources pretty simple, like university pages like Berkeley, and all of them just switched it up. In the Devonian, they were talking about Gondwana and Euramerica, and then all of a sudden the Carboniferous was Gondwana and LaRussia. So I looked into it, and based on my understanding, it seems that Euramerica broke apart, and one of those new fragments was LaRussia. Necessary context? Probably not. You don't need to remember that, because at the very end of this period, all of the continents finally came together to form the one and only. You know it, you love it. Super motherfucking continent Pangea. So keep that in mind. Throughout the Carboniferous, the continents are getting nice and cozy until at the very ends they form Pangea. So once the next period comes about, the Permian period, Pangea is absolutely kicking. So while these land masses were kind of slowly moving in as the backdrop of this period, the global climate was shifting pretty significantly as well. The early Carboniferous period was real swampy. That's a mourning dove. I don't know if you can hear it in the microphone. The early Carboniferous was real swampy, wet and humid, tropical. Think of Florida on a larger scale, with creatures that seemed like Florida inhabitants as well, that I'll show you in a minute. And then as this period moved along, the climate generally got cooler and drier. Think more temperate, maybe? There were more climactic fluctuations due to glaciation at the poles. So the shift from warm and humid to cool and dry led to some pretty serious adaptations in many groups, including in our ancestors, that I will show you in a minute. You might have heard the Carboniferous period be referred to as the Age of the Insects, because insects and other related groups were going absolutely nuts during this time, with some getting to the biggest sizes the world has ever seen, that we know of. So to understand why insects and other related groups got to godforsaken sizes during this period, we first have to check out what was going on with the flora that made their home all nice and cozy. Back in the Devonian period, the world saw the first large trees and forests that we know of. And now, in the Carboniferous, the plants are getting comfortable. They're taking shit over. The beginning of this period was real tropical, swampy. Plants were loving it, and they took on some forms that, based on fossil evidence, were absolutely sick. So, let me introduce you to a few of them. One of the most well-known and abundant trees during this time was Lepidodendron, also known as the scale trees. As far as we know, they could get to over 100 feet tall, with trunks that could get to 6 feet across. I came across some sources that said they could get to 180 feet tall, and then a couple other sources with like 130 feet or like somewhere in between that. So just know that's the range we're looking at across different sources. The scale trees loved swamps. They grew pretty densely all over them and were one of the biggest components of these swamp forests that we know of. They were made up of a single trunk that became branched at the top as an adult, with long, thin leaves that covered these branches and finished off with little cones at the very tips, like little Paleozoic ornaments. Absolutely sublime. Their trunk was covered in small diamond-shaped leaf scars, which were left all over them from shedding their leaves. And those scars, in some cases, became fossilized and eventually allowed us to identify them as fossils today, which is pretty insane. And like Wadiza and some of those earlier forms in the Devonian, scale trees used spores to reproduce rather than seeds, like ferns, fungi, and algae used today. Another tree from this time that's closely related to Lepidodendron is Sigillaria. Doesn't sound right, but that's apparently how you pronounce it. Sigillaria. They're both lycopods, and both had those diamond-shaped scars from fallen leaves. Sigillaria also got to over 100 feet tall as well. I would kill to see one of these in person, dude. I like this one a lot. If anyone knows how I can get my hands on a plant that looks like this, please let me know. I feel like there's got to be some sort of weird, fucked up succulent tree that kind of looks like this, you know? I feel like all those succulent trees kind of look like prehistoric trees. I love them. All right, moving on to a group of seed plants during this time. That's right, we've got some fucking seed plants during this time. Cordaites, a genus of trees and shrub-like plants with some members that could get to, you guessed it, over 100 feet tall that we know of. They had more leathery, strap-shaped leaves and were found in, you guessed it, swamps. It was Swamp City back in the day. But fossil evidence suggests they also tolerated a wider range of environments. The swamps, the mangroves, the floodplains, and also the upland forests. You name it. They were kind of up for everything, all over it. Some smaller specimens of Cordaites show evidence of aerial roots, which are exactly what they sound like. Roots exposed in the air, like the roots of mangrove trees. And the last one on the plant list is Colomites, a tall, hollow-stemmed plant, closer related to modern horsetails and kind of had a similar appearance, but much, much bigger. It had jointed hollow stems with needle-like leaves that came out of branches from the nodes on these stems, and seemed to have been able to reach heights of, you guessed it, 100 feet tall, that we know of, and lived in, you guessed it, swamp! I've definitely seen a succulent tree that looks like this one at the Oregon Zoo when I was there in November. They had all these little labels for all the plants they had on site, but they didn't have one for the one plant I wanted to get a name for, and I've been thinking about it ever since. It looked like this, and I don't know if it was a succulent. It kind of looked like if a pine tree was a succulent. I don't know if that makes sense. I'm way out of my comfort zone right now. But if anybody who has been to the Oregon Zoo knows what I'm talking about, please let me know, because I want one. Please tell me. Anyway, that was a very brief introduction to the plants that were alive during this time. The point is, plants were thriving. With a capital T. The world was absolutely lush, in a way it had never really seen before. So much so that their existence literally changed the concentrations of compounds in the atmosphere by a fuck ton, leading to those super high oxygen concentrations. So let me quickly break down why. I promise this is important before we get to the big insects. So, we all know photosynthesis. Plants take in sunlight, water, and carbon dioxide to make oxygen, which is released back into the atmosphere, and also sugar, which is stored in the plant and has all the carbon from the carbon dioxide. Gian, can you pull up a chemical equation of photosynthesis? So see, all the carbon from the carbon dioxide is in the sugar. 6 on one side, 6 on the other. This is like the only thing I got out of my chemistry classes in college. So all that carbon's sitting in the plants, and those plants are sitting in the swamp. When the plants died, they sat in these swampy conditions, which notoriously just don't allow materials to fully decompose. The whole thing with swamps. Also, fossil evidence suggests that the microbes that break down lignin, which is a key substance of these newly evolved plant structures, had not evolved yet. So lignin was just not being broken down. There was nothing to break it down. So these massive plants would sprout up really fast, pump a ton of oxygen into the atmosphere, pulling carbon dioxide out of it through photosynthesis, die, and then just pile up, meaning the carbon wasn't being released back into the atmosphere. So then, boom, oxygen concentrations were just fucking cruising on a highway to hell, about 30% compared to today's 21%. And this was sick for a lot of insects. It allowed them to grow to much larger sizes because of the way their respiratory systems work. Oxygen gets diffused directly into the tissues, so the increased oxygen made this efficient as fuck. This wasn't the only reason why some species got super big, but it was definitely a component for some. And also, not everything was giant. Actually, most things weren't giant. There were normal-sized ancestral grasshoppers and katydids, roaches, terrestrial scorpions that appeared for the first time in this period. There was a rapid diversification of flight, which, as of right now is kind of a jarring jump in the fossil record, like I talked about last time. Devonian fossils are like no flying insects, and then Carboniferous fossils are like
I fly now?
a shit ton of different ways that these insects are flying, so that's just what the fossil record is right now. Evidence of metamorphosis appears here for the very first time, and also terrestrial snails, which aren't insects and not even arthropods, but wanted to mention that, didn't know where else to put that. But let's talk about the big guys. Often when people think of the Carboniferous, they think of those big dragonflies. That's what I think of. And the big trees. One of the most well-known dragonflies from this period is Meganeura, one of the largest flying insects to ever exist, that we know of. They had a 2.5-foot wingspan, which, to put in perspective, your bedroom door is probably 3 feet wide. They also have the same wingspan as a broad-winged hawk, and also a small gull. In other words, this was a big-ass dragonfly, technically a griffinfly, which is morphologically slightly different. As we all know, nature doesn't give shit to you straight. Their larger size likely meant they had a wider variety to choose from on the Paleozoic menu. Lots of the smaller insects and other invertebrates, maybe possibly some amphibians as well. Fossils of their relatives, like other giant griffinflies, suggest they must have had to live in more open habitats rather than super dense forested areas, because their wings would have just fucking knocked into shit all the time. Or maybe they did live in a dense forest and they were just all sorts of fucked up when they were bopping around. Who's to say, really? Another one with a similar vibe to Meganeura is Mesotheris enormis, named such because they were, you guessed it, enormous. There have only been partial remains from a single fossil found, but it displays enough evidence to say that they had a wingspan of nearly 2 feet long. They had unusually long cerci, which are paired appendages at the end of the abdomen of many insects. Some serve as sensory organs, others pinching organs, weapons, sex organs. Depends on what kind of freak the insect is. Not incest, though. That's cerci, not cerci. As for Mesotheros, the purpose of their cerci is unknown at this moment in time. Alright, now, just so you know, we're moving away from the insects and into their relatives within the general terrestrial arthropod group. Fuck it. Let's do the arachnids first. Allow me to introduce you to Pulmonoscorpius, one of the largest scorpions to ever exist, that we know of. The largest fossil remains so far represent an animal that could get to 2 feet and 4 inches long. You know what else is 2 feet and 4 inches long? A Canada lynx. This scorpion was about the size of a Canada lynx. I worked with a Canada lynx once, named Ramsey. He was rescued from a guy who tried to buy him as a pet, and Ramsey kept ruining his furniture and his condo, as a wild animal does. So Ramsey didn't like people very much, but he liked cardboard. He liked cardboard boxes. One time I made him a little cardboard box boat, called it the SS Ramsey. He really liked it. I bet he's sitting in a cardboard box right now. Anyway, sorry, that was a little break from the Canada lynx-sized scorpion that we're talking about right now. Unlike modern scorpions, which generally rely on mechanoreceptive senses for prey capture, Pulmonoscorpius seems to have relied on their eyesight much more. They had proportionally much bigger eyes than today's scorpions, which maybe makes them cuter. Like, they're kind of baby for that, but their size, dude, can't get past it. For a while, it was unclear whether they were just another sea scorpion, which we're all familiar with at this point, the Eurypterids. The Eurypterids are very different than regular scorpions. They actually shouldn't even be called sea scorpions because they're not the same thing, but there was confusion nonetheless. Turns out 2 specimens of Pulmonoscorpius show evidence of book lungs, which are air-breathing organs that land-dwelling arachnids tend to have. So boom, terrestrial scorpion, arachnid, not a Eurypterid. I actually have an example that's the complete opposite of Pulmonoscorpius. That was originally thought to be an arachnid, but turns out is a Eurypterid. It's called Megarachnid, alive during this time. It was initially thought to be the largest spider to ever exist. Actually, people still mistake it as the largest spider to ever exist. It wasn't. It was 1.5 feet long, Eurypterid. The largest spider to ever exist, that we know of, is actually alive today. The Goliath bird eater, known to eat birds, largest by size and weight. They're about 1 foot long max. And up there with them, but a little bit lighter, is the classic godforsaken huntsman from, you guessed it, Australia.
What's he gonna do with him?
But enough about them, and on to our next arthropod on our lineup, Hibbertopterus, a sea scorpion, Eurypterid that looks like some sort of horseshoe crab, and also a strange shrimp. Kind of a funny looking guy. By the looks of them, you're probably thinking they were about the same size as a horseshoe crab, maybe a backpack-sized Eurypterid. Nope. Fossil evidence suggests the largest Hibbertopterus individuals could get to nearly 6 feet long. 6 feet long, dude. That's unnecessary for their shape, in my opinion. I don't mean to body shame them, but that just doesn't sit right with me. It's not scary, you know? It's just simply not right. It's like, I don't know about that. Their body shape with no context doesn't scream large to me, but maybe I'm just ignorant. Here's something that'll probably freak you out a bit. Hibbertopterus was a sea scorpion. Yes, a Eurypterid. But evidence of trackways that could only belong to them suggest that they spent at least some time on land. I don't like the idea of that body shape, of that size, walking around on land. You know? That just doesn't sit right. I'm sure you agree. This 6 feet long, on land? Yeah, no thanks. But the last one on our giant arthropods list kind of blows them out of the water on that front. It's probably the arthropod you've been waiting for, Arthropleura, a massive 8-foot-long arthropod that holds the record for the largest terrestrial invertebrate to ever exist, that we know of. So here's the deal. Arthropleura is often considered a millipede. Makes sense, you know? The massive millipede, the biggest fucking millipede. I've probably said that. But they weren't technically millipedes, just millipede-like myriapods, which is the group millipedes belong to. So, millipede by association. Remember, the millipede form has been very successful. Don't you fucking forget. Do you remember Pneumodesmus pneumoni, the earliest animal on land that we have direct fossil evidence of? Millipede form. In today's video, Arthropleura. And in modern times, we have millipedes that produce their own cyanide as a weapon. And millipedes in Australia actually have over 1,000 legs, because of course they would in Australia. Back to the millipede by association we're talking about today, the big one. How exactly they were able to get to this size is definitely due to a lot of factors. Diet being a big one. They likely needed lots of ultra-nutritious plant matter, and they might have even fed on other animals on land at the time, which wouldn't have necessarily been difficult for them considering they were some of the largest animals on the planet, walking the planet at the time, that we know of. Even bigger than many terrestrial tetrapods. Which brings us to the tetrapods. So last time in the Devonian, the vertebrates finally made it to land. It was the end of the no-bone zone.
No-bone zone.
And they did not waste any time getting established in the Carboniferous. Along with being considered the age of the insects, the Carboniferous is also known as the age of the amphibians. So let's go over what they were up to now. Starting off with the temnospondyls, a group that was fucking all over the place. They're considered proto-amphibians, so not true amphibians, and maybe potentially the ancestors to modern amphibians. And they were very much taking advantage of the newly established land. Lots to see. Some species were smaller, like centimeters long, and the largest could get to almost 10 feet long. Some seem to live their lives almost fully, or sometimes you write something in the script that sounds like you'll be able to say it right when you talk it, but then you can't. Some seem to have lived their lives almost fully or fully in the water, while others seem to be fully down with land. But all of them, as you would expect from proto-amphibians, still relied on water to lay their eggs in. Moving on to a specimen in a different category. The most well-known amphibian from the Carboniferous is Diplocaulus. Obviously, its boomerang head is a crowd pleaser. There are a few different species of a few different sizes, with the largest getting to about 3 feet long. They seem to have been more on the aquatic side of the amphibian spectrum, where they likely fed on small, aquatic creatures via ambush attacks. What exactly their boomerang head was used for is still uncertain. Lots of different ideas have been thrown out there, from defense, hydrodynamics, mating displays, or possibly somehow helping to funnel prey into their mouth. Exploring each of these possibilities is not really what I'm interested in at the moment though, because something else happened during the Carboniferous that would change the tetrapod course forever. What is a trait that the tetrapods we've gone over don't have that would have been necessary for the development of the lineage as we know it today? If you want to, pause the video. Try to take a second to guess what I'm about to say. You don't have to. Can't make you do anything. Actually, I'm gonna grab an example of what I'm talking about, so you gotta wait and think about it anyway. I'll be right back. I'm gonna be gone. An egg. Specifically, an amniotic egg. As you can see, this egg is very different than the eggs in the chia pudding that we talked about in the frog video, and also very different than fish eggs or other eggs in marine environments. This one's unfertilized because I got it from Trader Joe's, so it's really just for the visual aspect, but it will be useful nonetheless. So the classic fish egg or amphibian egg or any other egg is typically laid in water. They rely on the surrounding aquatic environment for the exchange of gases, nutrients, hydration, etc. The amniotic egg, on the other hand, has all that shit wrapped up inside of it. It has everything an embryo will need to develop. No need to be attached to a body of water. The shell does a decent job protecting the embryo from the elements, so they can be independent bitches. Bye-bye, ocean. I'm sure this is what the invention of the burrito felt like. Now I can take everything I want to eat and wrap it up in a protective shell and eat it wherever I want, go wherever I want with the burrito. No need for a fork, no need for a bowl. Got everything I need right here. And that's exactly what this amniotic egg allowed these newly evolved amniotes to do. Remember that during the Carboniferous, the global climate was going from wet and humid, cool and dry. Being able to lay your eggs away from a body of water opens up a huge variety of environments, a step that was definitely necessary for the survival of these tetrapods. On top of this adaptation, early amniotes also evolved water-resistant skin to prevent desiccation and diversified to shit. This was the root of the lineages that would lead to reptiles, birds, even mammals, who obviously would eventually keep the embryos inside the body. But we'll get to that in a few episodes. Alright, just leave it right there. Okay. It might seem like the path to these lineages that we're so familiar with today seems like a ways off still, but that is not the case. Because not only did amniotes first evolve in the Carboniferous that we know of, they also seem to have their first major split here into synapsids and sauropsids. Synapsids were the ancestors to mammals, and sauropsids were the ancestors to reptiles. And the evidence of this is in the bones, specifically the skull. Let's start with the synapsids, our ancestors. Behind the orbit, or eye socket, of all synapsids is a single opening called the temporal fenestra. It's thought to have allowed for the expansion of jaw muscles and opened up the ability to process a variety of foods. And now all mammals today have a single temporal fenestra behind each orbit, with a couple exceptions, I'm sure, since nature never gives shit to you straight. But the whole synapsid lineage that led to mammals can be traced using this single pair of temporal fenestra behind the pair of eye sockets, which is fucking sick, in my opinion. One of the earliest synapsids that we know of is called Archaeothyrus. It was about 20 inches long and had a sharp pair of enlarged canines, so most likely a carnivore. I know it kind of looks more like an ancestor to a lizard rather than a mammal, which is definitely due to that sprawling stance. That's like the OG trait for amniotes. This would eventually change to the legs underneath the body situation that we're more familiar with in mammals today. Another early synapsid from the Carboniferous, I think you're gonna like this one, is Adaphosaurus, a hefty fella. One of the oldest vertebrate terrestrial herbivores that we know of, and notable for the massive sail it had on its back, which might have been used as an early form of thermoregulation, maintaining the internal body temperature. That's what mammals do today, so that's pretty cool. Their form is probably a more familiar one to you if you've heard of their relative Dimetrodon, came a little bit later. We're gonna cover them in the next period. I fucking love them. I love the sail. But throughout time, Hollywood has kind of misrepresented them to be a dinosaur. Classic Hollywood shenanigans. Nope. These were synapsids, in the group that gave rise to the mammals, including us. Which is kinda nuts. This is in our distant lineage, rather than in the lineage with the dinosaurs. Okay, so what about the sauropsids? The ones that would give rise to the reptiles. What the fuck did they have going on? Well, like the synapsids, the key to the sauropsids was in the skull as well. The sauropsids had two different forms. The diapsids, which had two temporal fenestra behind the eye, and the anapsids, which had none. So, synapsids, one hole. Sauropsids, two holes, or no holes. The sauropsids have seen a shit ton of successful lineages. The dinosaurs, the pterosaurs, crocodilians, birds, I could go on. This is one hell of a group. So let me introduce you to some of its earliest representatives. First off, Hylonomus, one of the earliest anapsids that we know of. So they had no holes. They were about 8 inches long and kind of looks like lizards. They also had small, sharp teeth, which indicate a diet of insects that were abundant at this time. And next, Patrolochosaurus, considered the oldest diapsid that we know of. Another one that looked like a lizard, but this time with two holes behind the orbit. So we went over the age of the insects, got to the age of amphibians, and you might feel overwhelmed to find out that the Carboniferous is known as the age of another thing. Yeah, the sharks. The golden age of the sharks. Actually, more so shark relatives. This is the golden age of the wider group that includes sharks. One thing I've noticed science loves to do is be very generic when talking about what a shark is, like too generic, while simultaneously being very technical and being very exclusive of what a shark technically is. Let's do a little recap so you know what the fuck I'm talking about. So, back in the Silurian, the fish were going nuts. Chondrichthyes, the cartilaginous fish, first time popping up in existence, at least that we know of. Then they diversified into groups like acanthodians, the spiny sharks, which were not true sharks, but we still call sharks. And I forgot to tell you, in the last period, in the Devonian, a big shark thing happened, and I forgot to tell you. Two other major groups of chondrichthyans appeared for the first time in the fossil record. The holocephalans, also known as the ratfish, which have representatives today like chimeras and other ratfish. That's one. The other new group is the elasmobranchs, which includes sharks, skates, rays, sawfish, and their earliest representatives that we know of came from right about the middle of the Devonian. Phoebotus is the earliest elasmobranch, and Melanotus is the earliest holocephalan that we know of. Whoops. Sorry, I forgot about him last time. I know you bitches love sharks, so that's my bad. But anyway, now the Carboniferous is the golden age of the sharks. So allow me to introduce you to some of these golden age species, starting off with Dracopristis, an elasmobranch. It was first discovered in New Mexico in 2013 through an insanely well-preserved fossil specimen. It had a nearly complete skeleton, a body outline, and even soft tissue impressions, which painted quite the picture of what this species looked like hundreds of millions of years ago. Dracopristis was a nearly 7-foot-long shark, had 12 rows of teeth, sitting in extremely powerful jaws, and had a pair of spines on its back that were each over 2 feet long. They just so happened to look a bit reptilian, even though they obviously weren't, but definitely reminded the researchers of the reptilian form. So at the time of its discovery, they nicknamed it the Godzilla shark. They didn't know if it was a new species, or if it belonged to a different species. Well, they figured it out. They were like, fuck it, looks like Godzilla. Let's call it Godzilla. And in 2021, it was finally identified as its own new species. and given the scientific name Dracopristis, which translates to dragon shark. So, kind of the same vibe. It seems as though their large reptilian spines were used as defense against predators or other large sharks alive at the time. And despite their dragon or Godzilla-like appearance, they didn't seem to function as an apex predator based on their fossil characteristics. Their jaws suggest a lifestyle of not bottom feeding, but feeding on the bottom of lagoons, eating small vertebrates and crustaceans, like a chump. Alright, moving on to the holocephalans. You're gonna recognize the next two if you watch my video on the fucked up prehistoric sharks. This was the time of the fucked up prehistoric sharks. First up, Adestus. Not asbestos, Adestus. Also known as a scissor-tooth shark, due to the arrangement of their tooth whorls that kind of looks like a pair of godforsaken scissors, like Helicoprion's buzzsaw jaw. But two of them. By the way, Helicoprion technically did first appear in the Carboniferous, but it was their time to shine in the Permian, so gonna hold off on them until then. As you would probably guess, scientists initially speculated that Adestus used their scissor-tooth whorls like scissors, slicing prey right in half. But new studies with more advanced technology tell a different story. It's the same situation as Platypelodon's shovel map. Just because a part of an animal looks like a man-made object does not mean that it was used like that man-made object. No. Adestus seems to have used its tooth whorls to slash prey up and down, or snatch and slice, then pull the prey into its mouth using its lower jaw whorl. Regardless, it was heinous, and the size of their tooth whorls suggests that they could get to over 20 feet long, which is just woof. Alright, the next one is actually pretty cute. Stethocanthus. A smaller ratfish that could get to 2.5 feet long, and is known for the ironing board dorsal fin. The technical term for this ironing board dorsal fin is the spine brush complex. Brush, referring to a layer of placoid scales they had on the top of their dorsal fin and also on the top of their head, like a little toupee. The purpose of this complex? Uncertain, but the possibilities are deviant. And you know what? I'm gonna leave you on a cliffhanger. If you want to find out what those possibilities are, check out this video on fucked up prehistoric sharks, available on my channel, linked above and also in the description. Yep, you gotta engage with my content. Sorry, I don't make the rules. And also because I want to introduce you to a couple little guys that I haven't introduced you to before. Like this one, Falcatus. Another very small holocephalan that got to about 10 to 12 inches long. They also had a very strange dorsal situation, a little spine growing off the top of its head in the forwards direction. Scientists think this was likely some sort of display feature that possibly played a role in mating, and their big-ass, cute-ass eyes suggest they were adapted to deeper water hunting, maybe like my son. And another one, Iniopora. Very cute. Another holocephalan. That's all I have to say about them. So, nice. Don't think I forgot about the trilobites. But I don't have much news. In the Carboniferous, they were kind of starting to become less relevant. That's all there is to it. They were the extras in the feature film. Now let's move on to some more main characters. The strange specimens I know you've been waiting for. As we have already seen from the numerous species I've introduced you to from this period, things were just generally strange as fuck. So strange that they made up their own categories, rather than just another bullet point in the strange specimens list. So that means the ones I have left are just freaks. Absolute misfits. Let's start off with the most famous Carboniferous misfit, the one that was actually the topic of my first YouTube video ever, the Tully monster. Scientists don't know what, don't even know vertebrate or invertebrate. Do you know how fucking weird you have to be, where scientists are absolutely stumped on whether or not you have a backbone? That is all sorts of fucked up weird. So let's talk about what they got going on. They had a trunk-like snout with a claw at the end. That's their mouth, and it had 2 rows of teeth inside of it. They also had eyes on stalks that extend sideways, a combination of traits not even remotely seen on any other animal, which has led to a decades-long debate on what the Tully monster is in the most generic sense, vertebrate or invertebrate. What is the Tully monster? The conversation started on the invertebrate side, as you would guess. None of the thousands of fossils found showed evidence of a backbone, and it stayed this way for a while. But then, in 2016, different research teams went off, using different kinds of technologies like synchrotron, elemental mapping, fucking lasers and shit. One team found evidence of a notochord, a vertebrate trait, and gills, another vertebrate trait, so maybe a jawless fish. Another team found melanosomes in the Tully's eyes, which is another vertebrate thing, so another point for the vertebrates. But another team suggested the eyes were simpler structures called cup eyes that are found in certain invertebrates. A few years later, there was a test on the zinc to copper ratio in the eyes, which suggested invertebrate. But then a team using lasers found keratin, which is a vertebrate thing. So long story short, nothing is settled.
That's all, folks.
The argument is still hot. Nobody knows what the fuck it is. The other misfit on this list kind of has the same situation, called Typhlosis, also known as the alien goldfish. They were very small, about 3.5 inches long. And like the Tully monster, Typhlosis could be a vertebrate. It could be an invertebrate. They had no fins, other than a little blade-like looking thing on their end, seemingly no backbone, no eyes, no shell, no anus.
What?
Yes, you heard me right. Only one hole for everything. This is nothing new in the animal kingdom. There are plenty of beings with only one opening. Jellyfish, notoriously, and other cnidarians like corals and sea anemones. Planarians, dude, look at a diagram of a planarian. Look at where their mouth is. Anyway, it sounds crazy, but it's not really crazy in the animal kingdom. So with all these qualities combined, scientists were like, what the fuck is this?
What are you?
And took a closer look in 2022. They saw what appeared to be some sort of toothy structure in the creature's fossilized gut, similar in appearance to the molluscan radula, which is like if you had a razor for a tongue that you shot out before your food even hit your mouth so that it's all cut up and shit. That's what a lot of mollusks are up to. Now, it might have been what Typhlosis was up to as well, maybe a mollusk, but there's a lot more research that has to be done. So I want to go back to what I talked about with the plants at the beginning of the video. Remember, the oxygen concentrations were so high because the amount of plant material that sucked up all the carbon dioxide, with very few ways for that carbon to decompose and get sent back into the atmosphere. This was not only significant for life alive at this time, but also huge for humans alive today because of what this plant material turned into over millions of years. To explain this more, I decided to bring on a really good friend of mine who knows more about coal than anyone else I know. The one and only Milo from Mini Minuteman. There's a good chance you were introduced to me through my collaboration with him on his channel back in 2022, before I even started making long-form content. He got me in touch with his editor, Gian, who's down to help me get started and has been editing for me ever since. And so I owe my introduction to YouTube to him. I genuinely don't know where I'd be without his help and without Gian because he does an unbelievable job bringing these videos to life. So I was stoked that I was able to track down Milo for this video. He's been traveling all over the world and just so happened to land in the perfect place at the perfect time for this collaboration. So without further ado, here is Mini Minuteman.
Whoa, who's this guy? This doesn't look like Lindsay. Howdy, friends. My name's Milo Rossi. I am a science communicator here on YouTube specializing in archaeology. This is what I get for not charging my lav mic. The bird ambient noise is nice, the truck's compression braking aren't. And the reason I am in Lindsay's video today is because I am standing on top of the remains of these carboniferous swamps. Today I am in Tamaqua, Pennsylvania, located in the lower northeastern region of the state. And while I'm sure Lindsay is doing an incredible job telling you about the paleo environment of these unbelievable forests, I want to quickly whiz you about 330 million years into the future to tell you how these ancient forests played a very important role for everyone's favorite species of great ape. The immense, highly productive forests of the Carboniferous period would drop all of their natural debris on the ground, and year after year this would... Wow, they just don't let me talk about peat bogs anymore. And year after year, all of this natural material would build up to create a substance known as peat. Now, extrapolate that out for the hundreds of thousands of years that these forests existed, and you end up with some of the largest peat bogs that the world has ever seen. Time goes on, the Carboniferous forests come and go, but the peat bogs remain. They get covered by debris, continents collide with one another, and are ripped apart. And over hundreds of millions of years of geologic heat and pressure, the enormous peat bogs are transformed into the dense, black, highly flammable, carbon-rich material that we all know and love as coal. In fact, it is the coal deposits left behind by the Carboniferous coal forests that give the Carboniferous period its name.
Come a little bit closer. I'm all alone.
Yeah, okay, that's almost professional. We need to talk about coal. There are three different types of coal: lignite, subbituminous, and bituminous. Each type of coal being categorized by its carbon percentage, which dictates how well it burns. The lowest tier, the F-tier coal, is lignite. It's the least developed of the coals, only really a step away from peat, and has a carbon percentage between 25 and 35%. A little bit above that, we have the mid coal, which is the subbituminous coal. It's a little bit more developed than the lignite and has a carbon percentage of about 35 to 45%. And then above that, we have the most common type of coal, the A-tier coal, which is called, as you won't be surprised, bituminous coal. It burns hotter and longer than the other two with a carbon percentage between 45 and 85%. And both bituminous and subbituminous coal each made up 45% of the coal mined in the United States in 2022, making these two some of the most widely harvested and most common in the world. But I lied. There's actually not three types of coal, because above these three very common ones, there is one type of coal that is incredibly rare but changed the face of our planet. It is a name that has become synonymous with the Industrial Revolution and is responsible for putting northeastern Pennsylvania on the map as a major manufacturing hub. That is, of course, anthracite coal. Ah, man, I'm actually kind of glad I'm using a shotgun mic because the train whistle in the back could not be more perfectly timed. The god-tier coal, known as anthracite, is between 85 and 97% pure carbon, and it is one of the most energy-rich raw materials we have ever discovered on our planet. However, it is incredibly rare, making up only 1% of the coal mined in the entirety of the United States of America. 100% of the anthracite coal mined in the United States in 2022 came from right here in northeastern Pennsylvania, being the largest and almost only anthracite coal field in the United States and one of the largest in the entire world. It's shiny, brittle, and can burn at temperatures exceeding 3,000 degrees Fahrenheit. So why is it that not all coal is created equal? What is the magic ingredient that turns bituminous coal into the god-tier anthracite coal? Well, just like pretty much every geologic process, it is a lucky combination of heat and pressure. If you look at this region of Pennsylvania from the air, you can see that the land almost looks folded. This is called the Valley and Ridge Province of the Appalachian Mountains. It is a series of anticlines and synclines, geologic terms for folds in the Earth's crust. Over time, the different stones that these folds are made out of have weathered, creating these unusual cross-sections of the enormous folds created by the collision of the African continent and the North American continent. This mountain-building event was known as the Alleghanian orogeny, and occurred between 320 and 250 million years ago. This tectonic collision provided the necessary pressure to turn this peat into coal. But here in northeastern Pennsylvania, the pressure was just a little bit harder, and had the added ingredient of the regions nearby carrying volcanic activity. This added an immense amount of heat welling up from the Earth's core into the mix of the already massive collision of continents. Because of this, the conditions on this part of the Earth's surface were just right to transform the colossal peat bogs from the Carboniferous forests into the dense, black, energy-rich anthracite coal. Now, the reason that I'm here in Tamaqua today is because Tamaqua is still home to an immense amount of coal mining. Coal was noted by colonizers in these mountains as early as the 1690s, but it wouldn't be until the early to mid-1800s that the resource was being fully exploited. And the anthracite coal from northeastern Pennsylvania literally changed the world. As the budding United States entered the Industrial Revolution, it was the coal from the very mountains that I sit on right now that fueled the fires. They powered factories, built railroads, and won the Civil War. The job opportunities that this massive deposit of anthracite coal created, both in mining and manufacturing, saw a massive influx of immigrants into the United States, including my ancestors who emigrated to the United States from Italy in the early 1900s. They, like many other immigrant families, worked in the anthracite coal mines, backbreaking labor done in pursuit of the American dream. The overgrown coal tailing pile behind me is a relic of this era, a time when northern Pennsylvania became the generator for the blossoming United States, allowing it to become the economic and industrial hub that powered it through the Industrial Revolution. Today, much of the anthracite coal in northeastern Pennsylvania has been vastly depleted, with events like the Knox mine disaster bringing an end to an era, with small pockets still mined, but humanity has begun to transition away from it as a resource in hopes of finding things that are more environmentally friendly and less destructive. But all of that is to say that we have one major thing to thank for our rise to a global superpower. And that is ancient primordial swamps that existed 330 million years ago. Well, that's all I have to say, and there's a pickup game starting over here. So thank you, Lindsay, for having me on. Again, my name is Milo Rossi. Feel free to check out my channel at Miniman on YouTube, or you can type in Milo Rossi, you'll find me. Thanks again, Lindsay, and keep doing what you're doing. See you guys later.
So as you would probably guess from a process that was altering the environment to an atmospheric level, shit was not gonna end well. While this period didn't end with a major extinction, there was a minor one near the end of this time. It's called the Carboniferous Rainforest Collapse, and it happened about 305 million years ago. The gradual shift to cooler and drier climates meant that species had to adapt, otherwise they were gonna get booted. This might have been due to the higher oxygen concentrations kind of having a reverse greenhouse effect, but I'm gonna be honest, dude, the sources that I found for this collapse were kind of hard for me to get a good grasp on for some reason. Also, the formation of Pangea meant that all those coastal ecosystems at the merging points got squished out of existence, which I don't think is necessarily linked to the Carboniferous Rainforest collapse, but that definitely happened and is worth mentioning. Long story short, the shifting climate led to the need for species to come equipped with new adaptations. But the end of the next period was going to be the biggest test of all time. Let's get the global conditions out of the way. First off, we are finally fully at the full time of supercontinent Pangea. Remember, throughout the Carboniferous, the global climate was going from warm and humid to cool and dry. So the Permian was just Boom. Dry to an approximation. Because of Pangaea, we had one massive ocean and one massive slab of land that stretched all the way from the north to the South Pole. So everything in the middle of that slab of land was dry as fuck. I can't even imagine what the equator was like. One of the great things about water is that it tends to have a moderating effect on nearby land. And the interior of Pangaea didn't have that, so shit was fluctuating like nobody's business in the seasonal sense. But luckily, plants were still doing their thing. As far as we know, land plants throughout the Permian were just starting to look more and more like plants today. Lepidodendron and Sigillaria were still around from the Carboniferous, but their 15 minutes of fame was over. The gymnosperms, i.e. the seed plants, were really cooking, and for good reason. Seeds are really resistant to environmental stressors and have nutrients for the plant embryo. So you can kind of think of them as the plant version of the amniotic egg that some vertebrates became equipped with last time. But seeds came first, probably sometime in the Devonian like I mentioned, and I would argue are even better than amniotic eggs, clearly more durable. I tried to quickly take an egg out of the refrigerator the other day for one of my recipes and squeezed it a little bit too hard and it cracked in the egg carton. So 1 point for seeds. So anyway, by the Permian, gymnosperms were the dominant land plants that we know. Some notable species from the time were Glossopteris, arguably the most famous plant of the Permian, Walchia, Peltospermoles, just some classic mega ancient plant material. I know this next section usually comes later in the videos, but I just want to get it out of the way now. The trilobites. They're still around.
Why are we still here?
Looking pretty much identical to what they looked like in the Permian. Over 200 million years of this, the queens of consistency. Like I had mentioned last time, they were slowly becoming less and less relevant. The couple mass extinctions they had survived had taken a toll on them, and they weren't what they used to be, but they were still here. I'm not saying something considering all the shit they went through. Now that we've reached the end of the Paleozoic era, there's a big shift in what the fossil record deems the icons of this period. In the Cambrian, we had a shit ton of invertebrates, weird ones. Same with the Ordovician and the Silurian, sea scorpions, etc. The Devonian did have that big vertebrate transition to land, but there was also still shit like Mimetaster, or as many of you called it, Mind Taster. Which one is correct? I don't know, doesn't really matter. And also shit like Gigolopterus. And then obviously the Carboniferous speaks for itself. But from now on, the vertebrates are the stars of the show. It is now the mega bone zone.
Read my lips, it's a bone zone.
That's not to say that invertebrates are suddenly not interesting. The fossil record just doesn't like them. Fossil record likes bones. Big, thick bones. Who knows how many insane invertebrate species we've just lost to the rocks. I mean, think of Deep Staria, dude. That jellyfish alive today. There's no way there's gonna be fossils of them 100 million years from now. Maybe of their resident isopod, but I digress. That's also to say that this video and the rest of the videos in this series are about to get heavily tetrapod. So, let's start off with the ones that are still attached to the water.
Ironic.
Allow me to introduce you to Eriops, a big-headed amphibian that lived in lowland pond, stream, and floodland habitats. They got to about 6 to 10 feet long and weighed up to 450 pounds, and had a pretty ossified, i.e. rigid, skeleton to support their massive body while they moved around on land. Fossil evidence suggests they still had their lateral line, that fish thing for movement in the water. So they probably hung out on land and then went dining in the rivers and swamps for delicious fish and other amphibians. They also had a mouth that was seemingly very suited for crushing, so their diet might have had some shelled creatures in the mix as well. Another amphibious icon of the Permian is Prionosuchus, which is quite gharial crocodile-like in form. Most specimens found have been 6 to 8 feet long, which is pretty intense, but the largest fragmented specimen ever found suggests a max length of 18 feet long, which is just horrific. Well, actually, some of the largest crocodiles alive today are about that length, so I guess it's just neutral by today's standards. Or, I guess if you didn't know crocodiles could get that big, then you got 2 horrific things for the price of 1. I don't know. Let me know. Unlike Eriops, who seem to have spent their time kind of 50-50 between land and water, Prionosuchus was definitely in water. Hydrophilic, if you will. Based on the lack of powerful limbs, they likely swam like crocodiles today, using their long, powerful tails to propel them through the water, while the limbs were more for steering and stability. Given their max size, they were potentially apex predators of the waterways, snatching up fish and other amphibians like nobody's business, which would have sucked for fish and other amphibians. The last amphibian in the Permian lineup was actually discovered just in time for this video. Kermitops, named after Kermit the Frog. Great timing if you ask me. Despite being named after the beloved frog, Kermitops was not a frog. Frogs did not exist yet, that we know of. Not until the next period. They were more of a salamander, but we don't really have any famous salamanders they could have named it after, so boom. Kermit the Frog. They were very small. Their skull is 3 centimeters long by 2 centimeters wide. And that's really all the information I have for you because they were literally described like yesterday, so that's all for now. Alright, moving on to the amniotes, specifically the synapsids and the sauropsids. Remember last time I mentioned sauropsid lineage gave rise to birds, and reptiles, and the synapsid lineage eventually gave rise to mammals. They were each getting their footing in the Carboniferous, kind of looked the same physically. You can kind of think of it as they were figuring their shit out together. Couldn't really tell them apart from each other, aside from the temporal fenestra. By the time the Permian came around, they were ready to brawl. They figured out how to establish themselves, and were becoming more and more different, diverging further and further away from their humble beginnings. This was the start to a kind of tug of war between the synapsids and sauropsids that continues to this day. Who's the top dog? Who's the underdog? Let's start with the sauropsids. I'm not going to tell you which is which yet. I'm going to introduce you to some of the key players of each so you can guess, and then I'll tell you. Ancestors to dinosaurs, birds, and other reptiles. Looked like lizards in their humble beginnings. So, let's see what they're up to now. One of the larger groups in the Permian were the pariasaurs, who, despite their name, were actually more of the jocks of this period. Massive, plant-eating creatures that had these huge bony knobs and spikes all over their body. Had their own built-in armor. They were just absolute tanks. Unlike most other reptiles of the time, they actually held their legs underneath their bodies rather than sprawled out. The classic reptilian stance is definitely sprawled out, like they just got caught being up to no good. Pariasaurs were not into this. Too heavy. Needed more support. Arguably the most well-known pariasaur is Scutosaurus, named after, you guessed it, the scoots all over their heads. Remember scoots from, is that the Cool Fossils video? I think it was the Cool Fossils video. Scoots, a heavily built animal indeed, with some individuals estimated to have gotten over 2,200 pounds, which is about the weight of a Ford Fiesta. The Permian also saw the first aquatic reptiles that we know of, that weren't actually true sauropsids, but were on the sauropsid side of the split, if that makes sense. The mesosaurs, not to be confused with mosasaurs who came later.
I hope it doesn't come back and bite me in the ash.
The mesosaurs were much more chill, and their proportions just didn't really make sense. They had long, thin skulls, long necks, huge, webbed hind legs, banana-shaped ribs, and a massive, laterally flat tail to swim around. They also had these pretty gnarly, needle-like teeth that scientists can't really compare to any animals alive today. Kind of like a dolphin, kind of like a gharial crocodile again, but not really. So what exactly their diet might have been is not immediately clear. But researchers in Germany decided to get to the bottom of this in 2022. They examined 270 mosasaur specimens. Not to be confused with mosasaurs who came later. All of different sizes and slightly different morphologies, and found in different areas that indicate different types of prehistoric habitats. The different habitats could have suggested different species, which previous studies suggested. But the result of this 2022 paper suggests the different size and habitats suggest different ages, different stages of life. That juvenile mosasaurs, mesosaurs. I hope I didn't say that at any other point. I did! Whoops.
Oh no! Anyway.
The juvenile mesosaurs spent their time near the coast as active predators, and then adults went further out into the open ocean with a more filter-feeding lifestyle. Whatever the case, that didn't last very long that we know of. Fossil evidence suggests they were only around during the early Permian, so an unfortunate evolutionary dead end. Alright, so the sauropsid team had big guys, aquatic guys, and also flying guys. Well, gliding, but in the air nonetheless.
This isn't flying, this is falling with style.
Coelurosaurus, absolutely darling. They had these elongated rod-like bones along the sides of their body that supported a wing-like membrane, allowing them to glide from tree to tree, kind of like a flying squirrel, or a sugar glider, whichever you prefer. They also had sharp, curved claws for gripping bark, so they could climb up trees, like coconut crabs today. Gliding as an adaptation just makes sense. Forests were getting more and more dense, and the trees were getting a bit crowded, not necessarily the place you would go to avoid becoming a snack. If the predator can climb too, you're screwed. So boom, glide away. Easy peasy. Now, on to the synapsids, whose diversity was absolutely nuts during this time. Some were small, insectivorous species, while others were large, apex predators, and some of the largest terrestrial vertebrates of the period that we know of. Let's start off with the most well-known synapsid of the time, Dimetrodon. You've probably heard of them before. They get grouped in with dinosaurs pretty frequently because of their appearance. I'm gonna guess it's a mix-up with Stegosaurus, but they were not the same as Stegosaurus. Not even close. Dimetrodon is iconic on its own. They've been featured in the Jurassic World TV show, probably Land Before Time, best show ever. They're also in those little toy sets they used to sell at Michael's. I specifically remember that. Any dinosaur franchise shit, I'm willing to bet Dimetrodon is in it at some point in time. But again, they don't belong there because they were Permian synapsids. They were like your great
3 weeks later.
grandfather's cousin, and they were totally and completely badass. They could get to over 12 feet long and had this massive sail on their back that seems to have been used for thermoregulation, i.e. maintaining a certain internal body temperature. Blood pumped into the sail could have been warmed up in the sun or cooled down in a nice breeze. And that sail makes for some of the sickest fossils I've ever seen in my entire life. Mark my words, I will be getting that skeleton tattooed on me. Get me that skeleton. Sorry, Mom. I'm not done. Before we get to the next synapsids, I have to address, you might be thinking, wait, what the fuck? When did thermoregulation become a thing? Or you might be like, what the fuck is thermoregulation? So you know, some people refer to animals as warm-blooded and cold-blooded, like cats are warm-blooded and snakes are cold-blooded. Hold on. Odie! All right, never mind. I was gonna grab the cat. Whatever. So cats are called warm-blooded because they produce and maintain their own internal body temperature. They are endotherms. Heat inside. Snakes are called cold-blooded because their body temperature depends on the environment. When it's colder, they are colder. When it's hotter, they are hotter. They are ectotherms. Heat outside. That's why Tino needs a heating pad. Ectotherms are the default, as you would probably guess. Invertebrates, fishes, amphibians, and reptiles are all ectotherms. Almost said endotherms. Ectotherms. Endothermic groups only evolved twice that we know of. Birds and mammals. With a few random exceptions, of course, because nature never gives shit to you straight. When exactly endothermy evolved in the ancestors to mammals and birds, i.e. synapsids and sauropsids, is still a bit of a mystery. For the synapsids specifically, it's thought the roots are somewhere in the Permian. So the ideas of the function of Dimetrodon sail have that in mind. But obviously, warm-bloodedness does not really fossilize. It's honestly a fucking mess. There's like different estimates using different indicators. The how and why of endothermy evolved is really interesting, and honestly something I would love to make a video about, but it is way too complicated for today. So, let me know if that's something you would like to see in the future. Alright, moving on to the next synapsid in our lineup. The one and only Catillorhynchus. Calling them tanks would be an understatement. They're estimated to have gotten to about 20 feet long, so about the size of a large Chevy Silverado. You might be thinking these reconstructions do not look correct. Their proportions can't possibly be right, especially looking at something like this lovely silhouette. Well, this is their skeleton. As you can see, their ribcage looks like it's part of a tunnel system. They were just built like that. Barrel-shaped bodies and small heads. That was their thing. And leaf-shaped teeth to chew on high-fiber plant material, which was then digested quite efficiently in the barrel. Just so you know, we have barely gotten started with synapsids, because during the Permian, a new group of them arose that would eventually give rise to the mammals, the therapsids. I know, sounds almost exactly like synapsids, but therapsids, a new group within synapsids. And now we are jumping into them, starting off with the top of the food chain. Let's play a little game. What do you get when you mix a pit bull and a snake and a saber-toothed cat? Get a thought in your head? You get this. A gorgonopsid, saber-toothed, predatory, therapsids. Yeah, we are not fucking around anymore. They're considered the dominant predators of the Permian that we know of, and included species like the classic Gorgonops, Inostrancevia, Rubigia, and Soroctonus. Badass names if you ask me. Gorgonopsids were juiced the fuck up. They used their saber teeth to deliver slashing bites to their prey and intimidate their competitors. Damaged and healed skulls suggest that Gorgonopsids also bit each other's faces. They engaged in face biting with each other. Absolutely horrific. Alright, for this next one, I want you to take a Gorgonopsid, picture it in your head, and then run it through the wash. Now it's disfigured, grotesque. It probably looks something like Ankylosaurus, one of the largest Permian predators that we know of that could get to 20 feet long. They had massive heads with bone-crushing teeth and surprisingly heavy bones, which led scientists to believe they must have been scavengers, maybe ambush hunters on a good day. So heavy that some scientists entertained the idea that they might have been semi-aquatic. But a study done in 2021 changed everything. Using X-ray imaging to digitally reconstruct its skull, scientists discovered that the brain and balance organs of Ankylosaurus were specifically adapted for agile hunting. So, the thought of this rhino-sized beast capable of active hunting is absolutely heinous, if you ask me. And also, this is what Frenchies look like to me. No offense. They're cute, but they are absolutely built like this. I'm warning you. Keep breeding them, you're gonna have a teacup version of this. Alright, this next one. If you're a fan of Pokemon, you're gonna love it. Bulbasaurus. Kind of named after Bulbasaur. Kind of. The scientists who named it in 2017 said it was technically named for their bulbous-shaped nasal boss. That kind of bony, extra lump on their snout. Bulbous. So Bulbasaurus. But they also did admit that the name wasn't entirely coincidental. I don't know why they had to be so coy, but whatever. Bulbasaurus was like a turtle and a pig mixed together, but was of course not either of those things. They had a sharp beak to cut through plant material, and that's about it. Just cute as fuck. Alright, the next one I'm gonna have to start off by giving you some context before I show you any reconstructions. They've been a bit controversial in the paleo art community. It's called Esteminosuchus. Esteminosuchus! And as you can see, it has a pretty gnarly skull. Looks like a Halloween mask, to be honest. It's real ghoulish. They had multiple sets of horns projecting off of different parts of their skull, which earned them their name, the crowned crocodile. Not crocodiles though, obviously. This, combined with the rest of their body, made them about 10 feet long. Since they were discovered in 1960, paleo artists have tried to come up with ideas of what they would have looked like in life, with the ghoulish skull in mind. Let me show you some of my favorites. This is outrageous. Here's another one. And this one just looks like it's up to no good. There's this concept that's talked about a lot when it comes to reconstructing extinct animals called shrink wrapping. You might have seen this go around Twitter a while ago or wherever you peruse the internet. It's a good visual example of this. Essentially the idea that a lot more goes into the physical appearance of an animal than just their skeletal features. Soft tissues, which are only seen as impressions in some of the most well-preserved fossils in the world, which are obviously very rare. Here's an example of what reconstructing an elephant, zebra, and rhino would look like without taking soft tissues into account. Yeah, heinous. That's not to say that all reconstructions of anything ever are wrong, or don't take soft tissues into account. They've definitely gotten better with time. It's really just about keeping it in mind. Are Asteminosuchus reconstructions the way they are because of shrink wrapping? Some of them for sure, but there are definitely some that seem more practical. Asteminosuchus! That's enough of that one. So we've talked about some synapsids. We've talked about the members of a group that arose out of synapsids, the therapsids. And there's one specific group of therapsids that you should hold near and dear to your heart. The cynodonts. Our great
One eternity later.
great grandpa, which means yes, we are also cynodonts, and also technically therapsids, and also technically synapsids. We wear a lot of hats. Let me do a little quick visual. I still have the whiteboard. Hold on one second. This is like the crab video all over again. We've got the larger group, synapsids. Inside of that, we've got therapsids. Inside of that, we've got cynodonts. Inside of that, we've got mammals. And inside of that, we have us. Necessary? Probably not. That wasn't necessary at all, but whatever. The cynodonts were a step further in the long line of mammalian evolution, which of course they were unaware of at the time, but you know what the fuck I'm talking about. They had a set of more mammal-like characteristics that live on in us today, like differentiated teeth, incisors for cutting, canines for piercing, and cheek teeth for grinding. The word cynodont means dog teeth, teeth like a dog. They also had a more mammal-like brain case, the case that encompasses your brain, and my favorite, a secondary palate. There's a good chance you're eating while watching this video, and breathing at the same time. You can thank the cynodonts for that. The development of the secondary palate allowed cynodonts and their descendants to chew and breathe at the same time. Split it up. You know how much it sucks to eat when you have a stuffy nose because you can't breathe? Thank the cynodonts, that's not your everyday reality. Apart from being groundbreaking, the cynodonts were cute as fuck. They came in a variety of sizes, but were generally understood to have hair, and a lot of them were really small, which is just cute. Whether or not they had whiskers is kind of where things get fuzzy. There's some evidence that cynodonts might have had them, but that's still up for debate. Whiskers today are found in marsupials, i.e. Australia, and placental mammals, which is everything that you think of as a mammal, the classic mammal. But whiskers are lacking in monotremes, which are egg-laying mammals, like the platypus and the echidna. Let me draw a little diagram. Okay, so mammals. Whoops. So marsupials and placental mammals are more closely related to each other than monotremes. Both of these two groups have whiskers. So it seems as though whiskers must have evolved within the common ancestor of marsupials and placental mammals. That common ancestor was alive in the late Jurassic period. But some papers have noted the presence of whisker pits in Permian age cynodonts, arguing they did have whiskers. So what's the consensus? There's none for now. More research must be done. At this point, you're probably thinking that was a lot of synapsids, lots of diversity. But one thing that the sauropsids had a leg up in was aquatic or semi-aquatic lifestyles. Some groups went back to the water. Well, joke's on you, I'm not even done with synapsids yet. And there are some that seem to have displayed semi-aquatic characteristics, possibly. Like Perplexosaurus, cute as fuck. Like Liliodorhynchus, closely related to Cotylarhynchus, which just makes sense. I wrote many pronunciations on the side of this script, and even one possible cynodont for Cynosuchus, maybe kind of like a fishing cat. And we're still not even done with the synapsids because I found a couple that kind of qualify as the strange specimens. So let's just keep the ball rolling. Allow me to introduce you to UNCAPPED mirabilis, just a fucking mouthful of a name, and potentially the oldest venomous vertebrate ever found. Telling you dude, synapsids were fucking on one during the Permian. I say potentially because the consensus has been reached on a shaky ground. So let me give you the whole rundown. Back in 1931, paleontologist Robert Broom describes UNCAPPED after discovering its remains in South Africa. He noticed a little depression, or fossa, behind each of its upper canine teeth. Robbie thought they possibly housed salivary glands. A year later, paleontologist
Franz Nopcha von Verschusilvash.
Let's call him Frank, because that name is wicked. Frank proposed that the fossa housed venom glands, i.e. spicy salivary glands. People loved this idea, understandably so. That is a badass hypothesis. So people kind of just went with it without looking into it very much. A few decades later, another scientist said UNCAPPED had deeply grooved teeth, deeply grooved canine teeth, which could have allowed it to deliver that venomous bite. But turned out that was wrong. He likely misinterpreted earlier drawings. But this misinformation was like the highway to hell for the scientific community. They were going for it, and they seemingly had evidence to do so. Fast forward to 2022. What do we have now? More developed technology. So what are we going to do with it? Micro CT scan some shit. Based on the scans, researchers determined that the fossi were either used for venom, which mixed with saliva and envenomated their prey as they bit, or the fossil were used for sensory organs. The venom hypothesis seems more likely, and somehow, after all the back and forth and the misinterpretation, seems the most likely reason to this day. Would I call it a consensus? Probably not. But if true, UNCAPPED would represent the oldest venomous vertebrate ever found, which is pretty sick. I know you're probably getting tired of synapsids at this point, and honestly so am I. I just have one more to introduce you to before we get to the next group of strange specimens on this lineup. Siminia, also known as the Permian primates, because they seem to have lived their life in the trees. Their bodies were about 20 inches long. They had a long, slender tail that was about 120% of their body length. They also had very large fingers and huge hands compared to their arms, with claw-like bones at the end of each finger. They even had their first digit set off at an angle, so kind of like an opposable thumb. Pretty cool. All right. That's it with the synapsids. I know that was a lot. I'm gonna be honest, I wasn't expecting it to go on for that long, but I kept running into species that I felt like I just had to include. And then there were a couple times that I thought I found another sauropsid, but it turned out to be a synapsid, like Bulbasaurus. But what are you gonna do?
You have no power here.
So, who was ahead in this tug of war during this period? I think it's safe to say that what I presented suggests that synapsids ran shit during this time. They were the dominant group. Did I maybe favor synapsids too much and not make it an even fight by human error? Probably. I like synapsids more. I'm not afraid to say it. I like our lineage more. And there's definitely something to be said about the fragile nature of the fossil record. It favors big, thick-boned animals, not tiny lizard-like creatures. One paper published a few years ago started to address this. The Permian has always been considered the age of the synapsids, but was that really the case? There are plenty of smaller synapsids that have been historically overlooked, and as more and more are discovered, they might end up taking over in terms of overall diversity. It was just a lot of lizard-looking things. They were still very lizard-like in shape. So me personally, I'm cool with it being the age of the synapsids, because they were weird as fuck and also cool. But let me know where you stand. And let's move on to a different group. The next strange specimen is another one of the most well-known animals from the Permian. We've actually talked about them before on this channel. So I wanted to bring on my good friend Christian, also known as Shark Bites, to give his own twist on this introduction. He's a marine biologist and shark scientist, and is the guy to turn to for everything sharks and shark relatives. If you've never seen his content, you're gonna love him. So I'm gonna turn it over to him now to introduce you to the last two strange specimens on this lineup.
Hi Lindsay, thanks for having me on the channel, and thanks for giving me the task of talking to you guys through some messed up Permian sharks. I'll admit my speciality revolves around living sharks, but you gotta love the extinct ones because they are downright odd. First then, I'm going to introduce you to this slippery eel-looking shark, Orthocanthus. Orthocanthus was a 3-meter long extinct shark-like xenocanthid that likely lived in freshwater swamp habitats throughout the Carboniferous and into the Permian period, which was somewhere around 250. Its name literally translates to straight spine, pretty aptly named for that fat-off spine on its head. Based on where paleontologists were finding fossils of this guy, i.e. North America and Europe, we know that it was probably an apex predator in the oily, swampy habitats of the northern hemisphere. Just looking at it, it's like a combination of frilled sharks, spiny dogfish, and bull sharks from today's oceans, which is a lethal combo. There has been some debate as to whether it was an obligate freshwater species, meaning it could only live in freshwater, or whether it was a euryhaline species, which means it can tolerate a wide range of salinities, kind of like modern-day bull sharks. But we do know for sure it spent at least some, if not all of its time in freshwater. From fossilized stomach contents, we can see that Orthocanthus likely preyed on amphibians and other fish species, including this little guy, Triadus. Triadus, which was another xenocanth shark, looked pretty similar to Orthocanthus, especially with that dorsal spine. And it turns out that Triadus and Orthocanthus likely had a predator-prey dynamic with each other, with Orthocanthus almost undoubtedly feeding on Triadus. We know this because Orthocanthus fossils have been found with the dorsal spines of Triadus lodged in their faces. Ouch. This is very similar to the modern-day sharks that have predator-prey relationships with stingrays, like hammerhead sharks, who just messed with the wrong stingray and got a barb to the face for their troubles. But that's not all Orthocanthus fed on. Oh no. In tough times, this prehistoric sicko likely fed on its own offspring. Yep, that's right, every now and again, Orthocanthus ate its own babies. Professor Mike Benton, along with his co-authors in 2016, analysed the contents of Orthocanthus coprolites, aka fossil poo. They knew that it was the poo of Orthocanthus because they had a funky-shaped corkscrew rectum, which meant their poo came out spiral-shaped, so it's relatively easily identifiable. And within those coprolites, they found a shitload of juvenile Orthocanthus teeth, confirming that they probably ate their own offspring. That's known as filial cannibalism, by the way, for those of you out there that for some reason were wondering what the definition was. The scientists aren't 100% certain on why they did it, but because freshwater swamps were being colonized by loads of freshwater fish, at points in time, resources in those areas might have become scarce, and Orthocanthus just adopted a mama gotta eat strategy. Grim. Now, I just mentioned to you guys about Orthocanthus poo being spiral-shaped, and that kind of nicely brings us on to this weird-looking dude. Helicoprion, the buzzsaw shark. You know it, you love it. It's got to be probably one of the goofiest-looking prehistoric shark species there was. On the technicality, we can't really refer to this guy as a shark because it was a member of the holocephalans. These are your ratfish. No, not like that. More like this. So Helicoprion was a distant relative of these cute little guys who hang out in the deep sea today. As we've heard in one of Lindsay's previous videos, Karpinski, known for his paleontology skills and strong goatee game, was the guy who discovered the first Helicoprion fossil. But because all sharks and their relatives, including the holocephalans, have cartilaginous skeletons, the only bit that was fossilized was these spiral teeth, and scientists at the time really had no idea where it was supposed to be on Helicoprion's body. So in true earlier 20th century fashion, we got some great scientific speculation. Take a look at this handy gallery of Helicoprion drawings and where they thought that spiral might be on the body. So we've got it on the back and on the dorsal fin. We've got it coiling up and out of the snout like some kind of lethal spiky fruit roll-up. It coils up and it coils down. This one here looks like he's about to celebrate New Year's Eve with a party blowout. We've got another one that looks suspiciously like a basking shark. This guy over here who's just pure hating his life. And then this one, where they just plonked the vortex of doom on the underside of a stingray. Were they high? You can see, though, the majority of them thought it was somewhere near the mouth. Kind of. But in 2013, some pretty clever scientists decided to CT scan the near-perfect fossil from Idaho and definitively proved that the saw was in the mouth, and specifically, it was in the lower jaw. And it was this discovery that really helped them figure out how Helicoprion used that impressive tooth spiral. If you were reading the scientific literature about Helicoprion, you'd be met with paragraphs of death like this one, which uses words like palatine ramus and ethmoid process. Instead, you guys are going to get the shark bites explanation. Contrary to their buzzsaw namesake, Helicoprion's tooth spiral didn't spin around in their mouths, chopping up everything in its path like a bad accident in a workshop. It was actually fixed in place, apart from when it was growing. J.B. Ramsey in 2015 suggested that because the spiral was shaped how it was, it couldn't feed on hard prey because hard prey would just slip out of the jaws. Try and cut a walnut with a pair of scissors and you'll get what I mean. So because of this, they'd feed on soft prey items like squid because they'd easily be captured and trapped by the tooth spiral. But it was also suggested that they fed on ammonites. Ammonites had hard shells though, so how did they eat them? Well, the Helicoprion would approach its ammonite prey with its mouth open wide. The soft body of the ammonite would be impaled on the tooth spiral, and as the jaw closed, those teeth would pull the soft body into the mouth and down the oral cavity, while the upper jaw would simultaneously close and push away the hard shell. Helicoprion would literally teeth slurp those ammonites out of their shells. That is grim. To help me demonstrate this motion, I've got a handy cutout of a Helicoprion head and jaw. And if you're asking whether I spent an hour making this on a Monday afternoon, you are absolutely correct. So you can see as the Helicoprion clamped down on its prey species, i.e. ammonites, which let's say are my head, how the teeth on the lower jaw could grasp the soft part of that prey species, pulling it further into the mouth, where the upper jaw and the head would push away any hard shells. Right, okay, that's enough demonstrating with that thing. I think I just wanted an arts and craft afternoon, really. So ammonites and Helicoprion were likely locked in this teeth-slurping predator-prey dynamic for a long, long time, as both of them somehow managed to survive the Permian mass extinction event, which wiped out the best part of 90% of all marine animals. But I'll leave that to the pro. Back to you, Lindsay.
So we've talked about many Permian creatures of different sizes, different lifestyles, some of the lesser known, and some of the icons. I haven't told you yet about the most iconic aspect of the Permian, the way it ended. Despite being the second most well-known mass extinction, obviously after the dinosaurs, the end Permian extinction event is known as the #1 most devastating of the Big Five mass extinctions. So much so, it has earned the nickname the Great Dying. It wiped out the vast majority of life on Earth, with the extinction of something around 90% of all species and up to 96% of life in the oceans. 96%, dude. This is seen in the fossil record as a drastic loss in representative species from the boundary of the Permian to the Triassic. Sea scorpions, completely wiped out. The spiny sharks, the acanthodians, wiped out. The trilobites, completely wiped out. We're done with them. The Great Dying was not fucking around. With a catastrophe of these proportions, as you would probably guess, there are plenty of hypotheses as to why this happened. What could have caused something like this? I'll break down a few of them that have evidence. The first, an asteroid impact. Of course, the idea of an asteroid has to be thrown into the mix. Geologist Gregory Redelec found quartz crystals with microscopic fractures in rocks from Australia and Antarctica that line up perfectly with the Permian-Triassic boundary. He said that pressure greater than a nuclear bomb would have been needed to create that type of quartz, and that could have only been from an asteroid. If true, the asteroid would have released massive amounts of toxic gases, blocking out the sun and causing temperature drops, acid rain, and darkness, and life doesn't like any of those things. Another theory points to a lack of oxygen in the deep ocean. English geologists Paul Wignall and Richard Twitchett found evidence of ocean anoxia in rocks that formed in shallow waters during this time. They suggested that a lack of ocean currents, possibly due to an absence of ice caps, could have allowed anoxic water to build up, spread, killing off marine life. So, maybe a component. But the most widely accepted theory is volcanoes, and there is plenty of evidence for this in Siberia. The Siberian Traps are a massive area of lava flows that cover like 1 million square miles and date to the end of the Permian. Apparently, the amount of lava produced would have been enough to cover the entire planet in 20 feet of it. That's a lot of lava if you ask me. But it wasn't just the lava that caused problems, it was the volcanic gases that were released at the same time. These gases would have led to the acid rain, the blocking out the sun, with sulfate molecules, which would in turn cool the earth. I know it probably seems like lava would make shit hotter overall, but no sun equals cold, and sun beats lava. This would have led to glaciers at the poles, which would have obviously sucked up ocean water, leading to lower sea levels, leading to the destruction of shallow water ecosystems. Pair that with the carbon dioxide from the volcanoes and organic matter being broken down, and boom, you've got a greenhouse effect. And a nasty one at that. Of course, it was probably a few of these scenarios that got served as a combo that led to the mass extinction. The perfect storm to cause the biggest catastrophe the world has ever seen, that we know of. But life still managed to find a way out of it. Obviously, we're here talking about it, and we're not even halfway through the series. This was probably the closest to the end of the world animals ever saw, but it was still not the end of the world. Every species alive today can be traced to an ancestor that made it out of the Great Dying, which is pretty crazy when you think about it. The world is unbelievably diverse. Millions and millions of species, and that's all because of the few that survived. And that brings me to the last species on our lineup that I want to introduce you to. I know, this late in the video is a bit jarring, a bit unsettling, but class is not over yet, so sit down. There's one animal in particular that's often talked about in the context of this extinction, and the fact that it made it out. Lystrosaurus. You guessed it, another synapsid. Closely related to Bulbasaurus, as you would probably guess from the beak, and also very cute. Like doomsday preppers today, they liked burrowing in the ground. Their mix of traits suggests they were built for arid environments, and the presence of closely spaced growth rings in the tusks of South African and Antarctic species suggests they might have been some of the earliest animals to hibernate that we know of. This combination of behaviors and traits ended up being very useful during the mass extinction. They were all over the place, and based on the fossil record in the early Triassic, they were the single most common vertebrate on land. But they were a dead end, as far as we know, because the process of recovery on Earth was not an easy one. It would result in a new wave of nature's trial run that included some of the most bizarre vertebrates the world has ever seen, that I'll be introducing you to in the next episode, the Triassic, so stay tuned for that. The Paleozoic era is over, so be sure to subscribe so you watch the history of life on Earth unfold. Check out my Patreon for behind-the-scenes updates and our Discord server, and for now, stay curious. The world has a lot for us to learn. See ya!
Get me Capitaine Dubois from Animal Control.
Speak. I do it. A lion? The moment I have been preparing for my entire life. The king of the beast.
Based on the fact she wants to get a lion head, we can assume this is not just animal control, but illegal poaching. The question we have to ask ourselves is, where did she kill these animals? Because, for example, in Kenya, you get a death sentence for poaching. She is going to Monaco. But as she says herself, she is French, and in France, poaching gives you a €450,000 fine for the first offence. Since she has done it multiple times, it will go up to a multi-million amount and a few years behind bars.
I am so happy to see you. You will not...
Deep cologne is obscuring the animal musk. Voila, giraffe at 12 o'clock.
Paparazzi! Here I am! No more pictures!
Monaco Animal Control. Perfect case record.
Hi, officer. Is there a problem?
Oh, watch out!
During the fish oil scene, she jumps over a car. Since she came from the right, she had priority, and the car was in the wrong. But she did end up driving the wrong way and on the sidewalk.
Deploy banana gun!
Driving in the staircase of a building and driving on roofs never really happens, so I guess I will just call it property destruction for the door. And the scooter crashed into the building.
That's it! I'm going in!
Lion. 12 hours old to be bozos. Ran away with the circus.
Illegal passing of the border and trespassing on the train.
Viva la France!
You're in a big trouble. Trouble?
Well, now you're really in a big trouble.
I know.
Get up. I'm going to have to send you back to Monaco.
The oldest trick in the book, Commandant.
A looking poster. I'm gonna hide up on the ceiling a trick. The secret of the tunnel under the bed. Let's go. The secret tunnel is a dead end. Was that the sound of a cell door closing?
Monsieur, we both know the lion does not belong to you. He's a fugitive from justice, so that I may put him where he belongs, on my wall.
If we go down in flames, so be it.
Hey, is my neck getting longer?
In a black and white movie,
Dubois.
Fit in the carry-on.
but his head will.
You brought back Alex the lion.
It's a miracle.
Thank you.
She did stun the animals, but they were on the loose in a zoo, so she will probably not be pressed for this act. But she again crossed an international border, though.
It was never about the money, the lion. I am going down. Your head is coming with me.
Your days of chasing animals are over, Dubois. Now sit.
son returns. This is perfect!
I thought you hated Zuba.
Oh, I do. I do. Use Alakay. Yes, I'm going to use him to get rid of Zuba once and for all.
All right, so just come straight from the heart. You'll never go wrong.
Sure, mister.
Hey, Alakay, I just happened to walk by. I thought I'd wish you luck. In my opinion, the key to this whole thing is choosing the right competitor.
Like a dance-off?
Sure.
Who do you think would be a good match for me? You know, just to keep things interesting.
I wish I could help, but that's strictly against our ancient tradition and all that we hold sacred. I choose Titsi.
Makunga, right? Thank you.
Anything for Zuba's boy. Go get him, Tank.
How about you? The tall, handsome one, right there, yeah. Choose your opponent.
Titsi?
Not dance, fight! What is he doing?
I know that boy is not dancing.
Turn around.
Horrible. Alakay has failed the test. Zuba would have to banish his own son. Sadly, the Alpha Lion must cast out all failures.
Then I'm no longer the Alpha Lion.
Dad, what are you doing?
Who could possibly take Zuba's place? No one?
Hey!
You, sir. I guess not. This is all very awkward, but I suppose I carry this tremendous burden. I hereby banish Alakay for 1,000 years, or life!
Makunga made a conspiracy to overthrow Zuba, the ruler of the reserve. He claimed himself it was against ancient traditions and everything sacred to help a prospect with their rite of passage, and did so anyway. So he basically set up Alex for failure and uses this to take over the alpha position. There was someone else who wanted to contend, but he smacked him down in the face. I will charge this battery, and on top of that I will sentence Makunga to usurping the throne for his schemes.
The water.
A watering hole has never gone dry before.
How did this happen?
Out of my way. What is going on here?
What do we do?
Quiet! Listen up. One solution to this horrible crisis. We'll all have to fight for it.
Well, that's not fair. You'd win.
Exactly, Shirley.
I'm bummed.
Looks like a clogged pipe, like we get in New York all the time.
You? I'd help you pack, but by the looks of that hat, I see you're all set. Maybe you should try a little rain dance. Ba-da-ba-da-ba.
Bus should be in charge, not you.
All right, fine. As an added measure, I will consult with Zuba. The watering hole is dried up.
Dried up? That's impossible. What are you going to do about it?
He's gone upriver.
Off the reserve?
No.
I tried to stop him. I told him it was suicide, but he was determined to prove himself to you. Hurry, Zuba!
He claims it is suicide and manipulates Zuba to do the same as Alex. But he didn't lie or do anything wrong, so this is perfectly legal.
Well. If I remember correctly, you quit, and you were kicked.
We humbly present you with this token of appreciation.
Yes, I think this would go very nicely for me when I go out hiking.
My handbag!
D3.
Right.
This vending machine kidnapped 4 of our beloved penguins, assaulted a cop, and destroyed a wall and roof. He is also trespassing the facility in the first place, and of course, not to forget, he stole the vending machine. You didn't go through border control.
Sorry, what?
That That weapon is definitely not legal.
Humans know me as Dr. Octavius Brine. You know me by a different, much older name. A shadow of a former life. Dave! You seriously don't remember me? I was the total package.
Wow!
And then you arrived.
Just smile and wave, boys. Smile and wave.
I finally have the power to destroy you. After them!
Here they come!
Right.
The Octos assaulted both the man and Skipper.
How about now?
Yes!
It's
over.
Show you this. We're just getting started.
Incoming alert. 15 penguins missing.
Dave's kidnapping other penguins!
Elijah, would you please take them away?
Shanghai. Hasn't been there yet, Skipper.
On the TV, we can see 31 zoos missing penguins. New York, one other zoo, and the 7 from Brazil already have been sentenced. That leaves 28 more zoos with an average of 5 penguins kidnapped.
Bingo! Nice try, Dave.
David the Octopus.
What?
Private!
If we keep the average of the 5 penguins per zoo, this are 30 zoos worth of penguins falsely imprisoned.
All I need is a test subject. Let a buggy do as I unleash the full power. Fire! I made a monster!
In life, don't let anyone tell you what to do.
Eva.
It's gonna turn us into monsters!
And what comes next, Dave? Invasion!
No!
I disintegrated him.
Oh, great.
Breaking news! The missing penguins have been found! Dr. Octavius Brine has found the penguins and is bringing them here to...
Penguin lovers of the world! Do it. Penguins!
Penguins! Penguins! Penguins!
What? Oh, the people love you. Just go give them a hug.
Mm.